All right, okay. Hello, everyone. Welcome to this RSS 2026 workshop on tactile sensing for robotic foundation models. It's really exciting to see, although I couldn't really see, but I imagine there's a room of people all sharing the interest in the direction of tactile sensing and robotics. And yeah, today we have a really amazing lineup of speakers. So I'm James. I'm a senior research scientist at Ant Group, and I'm also doing a visiting postdoc with Mark Cutkosky at Stanford. So unfortunately, I'm not there in person, but I'm really honored to lead the effort to organize this workshop. So for the first 5 minutes of this workshop, I'll just give a high-level overview of the motivation and what the program will look like, and then I'll hand it over to David to kickstart with our very first speaker. Right. So the motivation of this workshop is really simple yet compelling. So I think for the past 1 or 2 years, we have seen a lot of really exciting startups and also big tech companies building these various data collection devices to really scale up data collection, to scale up the data we have for robotics to train foundation models and world models. And then the question is really straightforward. So what role will tactile sensing play in this new era of big data for robotic foundation models, right? So we are broadly interested in a wide range of topics, including both hardware, questions like what tactile sensing should look like at scale, and also integration and system level questions, such as how touch will fit into the overall robotic stack. And also we are definitely interested in algorithms and model training parts. And the question is, how should the tactile modality be used in combination with other modalities? Should we have some shared common embeddings, or should we train on one modality first and fine tune on tactile modality, or what role should, or maybe we should have meta controller to switch between different modalities. So these are all interesting questions we are excited about. And hopefully after today's workshop, we can all walk away with some answers to maybe a subset of these questions, some takeaways. That would be the hope. So again, this is the schedule. It's also on our website. We have a great lineup of speakers. We also have 7 oral presentations, 5 minutes each from 7 submissions. We will then have the panel discussion where audience can have more interactive conversation with the panelists. Eventually, at the end, we'll hand out the best paper awards. Some stats about this workshop. We in total accepted about 31st papers for poster presentations. This is a fairly large number for a workshop, I think. Among these poster presentation, we selected 7 submissions to give oral presentations. And among these 7 oral presentations, we'll select the best paper award and 2 runner-up awards. A really big shout out to all the organizers. Without their hard work, this wouldn't be possible. Many of them couldn't attend in person like me, but this doesn't take away any of the hard work they contribute to this workshop. We do have 4 on-site organizers there to help. Maybe they can stand up and show their faces so people can recognize them. Finally, definitely not the least, last but not the least, we have 2 very nice industry sponsors, the Ray Institute and the Ant Group. Also, big thanks to them for sponsoring the Best Paper Awards and other, and basically everything. So now I'll hand it over to David to invite our first speakers.
I'll get started with our first speaker. We have Mustafa Mukadam, who's a researcher at Amazon's Industrial Robotics Group, also an affiliate assistant professor at the University of Washington, We're really excited to have him kick us off in this workshop.
All right, let's get started. Just on point to the theme of the workshop, I wanted to kind of re-question how do we actually advance robot dexterity and what that even means in today's landscape. So I sort of searched on YouTube how to use a screwdriver, and this is one of the videos that came up. Uh, you know, as anyone who might have used a screwdriver before, it is quite involved. You're applying a lot of forces, you're making intricate sort of multi-fingered movements, yet it still sort of somehow remains far from reach in terms of what robots can do today, right? Like there's a bunch of options. We could say let's do teleoperation and you know use our favorite foundation model VLA, but you might quickly realize that this is very hard to teleop. Uh, all right, like then, that's 2 years old news. Like what else could we do? Human videos seem hot, right? This is already on YouTube. Can we use that? Actually, it seems like that is also quite hard because we're missing a lot of like useful force and those kinds of information. So how do we actually get there? We could sort of do the other side of things where we are seeing progress in dexterity, which is use simulation and do sim to real, but that also seems challenging to scale because you have to design complicated rewards tasks per paradigm. So how do we actually break through that barrier? Like is one solution enough, or do we have to actually start thinking about like hybrid stuff? So that's kind of what we were motivated by when we were working on this paper a couple of years ago. It already feels sort of outdated because it was using Allegro. We were working on this in 2024. Back then, Allegro was kind of the hand everyone was using. That's definitely not true today. But we can do these kinds of tasks, and I think the key innovation here was realizing that actually, humans are really good at providing high-level information. So you could use that as guidance, and then use simulation to do the sort of low-level stuff and that was kind of one of the key innovations where we could sort of put the high level and the low level together. The other was to realize, we're really missing sort of the foundation model for dexterity. And the idea here was, can we think of a pre-training task where sort of more complex skills essentially emerge without you needing to necessarily train for those in a traditional sort of single task curated RL kind of pipeline. And over a lot of iterations, what we landed on was essentially this kind of any to any grasp kind of paradigm where essentially you generate a bunch of graphs across a bunch of different object shapes and then essentially train RL expert policies to just move around on those objects and then distill them into a single controller. And it turns out like you can just kind of deploy these with these kinds of like complex teleoperation plus skills task and show that you can basically do all of these things without ever even having trained on them. Essentially, because what you're exposing the policy to is kind of these like rich contact interactions, but not necessarily concerned about what the task necessarily is, because that high level information is what the human is going to provide in this setting. And that could be easily replaced by like a high level policy or a behavior. But then, building on top of that work, a lot of the new papers are also sort of thinking about the same idea. What is the kind of foundation model for dexterity? Can we leverage sim and then combine kind of the high level information from humans and kind of bring those two worlds together? But a common theme you will quickly start seeing as you go through these papers and kind of DexGen, which they're inspired from, is basically they're all missing tactile. Like if you go to the our paper or like any of these papers in the kind of future work section, you'll say like, oh yeah, we want tactile, we want it there. So what is kind of the deal? Like why isn't that happening? And then if it was happening, like why do we care? Because it seems like we can do all of these tasks without tactile. So like what is that really kind of buying us? The way I've sort of started thinking about this is really on an axis of how far hand is away from the context it's trying to control. And so as the degrees of separation increase, uh, my sense is the task is getting increasingly complex. So it's not necessarily that you can't do it. It's more that you become less reliable and slow at doing those tasks. And one of the things we saw was, in this work, neural fields that was led by Sudhu, uh, we can essentially combine vision and touch to estimate new object poses and shapes in real time as the robot is manipulating them. And a key observation we made in this work was essentially touch sort of acts as a supplementary thing for vision uh, at worst when vision is completely not available, and when vision is available it almost complements it. And that's sort of a key realization kind of in hindsight, where if you have a lot of occlusion, that's where tactile really provides kind of the value and also kind of adds to the robustness for the tasks you might care about. So the other thing you might see is like, yes, we can do these tasks, but we're only thinking about success, right? We're not thinking about, robustness, or we're talking about speed. Like these are all pretty sped up videos. We can do a lot better. We should try to think about how to do better. And so I think we should, as a community, start thinking about what is beyond success and how do we get to speed and reliability, which is actually going to make robots more useful. And in fact, we should be thinking about those two things together. And that's kind of what is commonly known in industry or automation is essentially throughput. And shout out to Pulkit, who recently gave a talk at ICRA making this exact same argument. That it's not that as a community we've been stuck in terms of figuring out this magic silver bullet task that, like, if only we can solve this, everyone's going to be convinced that tactile is useful. It's really just that tactile drives the throughput, and that same argument extends to multi-fingered hands as well. So now that we know where to shoot for in terms of using tactile, how do we actually get it to be used in policies? So we've sort of almost perfected this recipe over the last couple of years, doing tactile representations across kind of several different works. One with like flat sensors, another with skins overhaul dexterous hands, and also multimodal fingertips. These works were all led by Carolina, Akash, and Tausha. And what we found was essentially a kind of a straightforward recipe almost, where you take these sensors and collect large scale data sets in the real world. And you essentially care in these cases more about exciting the sensor across all of these different regimes instead of necessarily thinking about, are you getting the tactile sensor across all the tasks you care about, which sort of makes the problem easier, because what you care about in terms of this training paradigm or pre-training paradigm is essentially exciting the sensor across all of these. For instance, with a multimodal sensor, you want to ensure that you are, collecting tapping interactions or sliding on like rough surfaces and things like those, not just like doing touching and kind of going as you collect sort of one data at a time. So, that was kind of step one. You collect sort of these broad data sets, and then you just essentially apply sort of your, state-of-the-art self-supervision techniques from, established in computer vision, like masking-based self-distillation, similar to what people have done with Dino. And what we found was like we could just basically, train these tactile encoders with really large scale data without needing any sort of labeled data like forces and slip or things usually people would care about. This is sort of one of my favorite kind of results from one of these papers, where we essentially are able to sort of take a raw sensor, pass it through the encoder, and decode these sort of shear and contact fields entirely self-supervised. And another kind of interesting experiment was when you can sort of take these pre-trained encoders and decode put a lightweight decoder on top for solving a task, and easily transfer that decoder to solving it with a new sensor that it has never seen before on a new task, in a few short paradigm without necessarily needing to retrain the whole thing with really large data. And that's where kind of the power of a pre-trained backbone really comes and shines. But that's all in good, and we can understand kind of what these representations are capturing. But like coming back to the question of how do we actually use it in policies, we could start doing kind of the easy thing, I guess, where we essentially teleop and use our favorite behavior cloning paradigm and use the sensor data that was collected, and then sure we can train these policies to do sort of simpler manipulation tasks that are possible to teleoperate, and in some cases even show that having more sensory modalities on touch does help, and it actually improves significantly over just using a wrist camera. uh, but the question remains, right? Like if we can't tally off the tasks, and as we discussed, we want to build like sort of these foundation models building off of simulation data. How do we sort of bridge this gap between a model, a policy, or a foundation model for a policy built in simulation, while you have your tactile encoder that's built entirely in the real world with real sensors? So one of the things we did in this work was essentially look at kind of your state of the art kind of simple policy that can do in-hand object rotation. And at this point, this has been like pretty popular in terms of doing student teacher, RL and simulation, in using entirely proprioceptive data. And what we ended up doing was essentially deploying that sim to real and collecting a really small data set, like 30 or so trajectories of the same hand doing the exact same task it was trained in simulation, like the hand facing up and then just rotating the object. And what we did was take the pre-trained sort of tactile backbone and start with a zero convolution and slowly add that information into the base model, while keeping the kind of encoder and the policy frozen, and only training on a kind of a offline objective of the difference between the actual actions that the policy executed versus the desired actions the policy had predicted. And that signal alone is sufficient to sort of slowly start increasing kind of the contribution from this tactile encoder and kind of merging it with this pre-trained encoder that you have from simulation. And what we saw was essentially like that same policy with this extra kind of post-training adaptation step in the real world can start kind of improving the simulation policy that hasn't been trained on those kinds of variations, but is entirely using tactile sensor as the kind of feedback mechanism. So in this case, we can kind of add additional weights. We can even kind of put tape and change the frictional properties of the object, and continue to see more robustness, even though in simulation none of these have been actually trained to do those. We can even change the orientation of the hand, which is definitely not something we had done in simulation, but the policy still remains robust to that once the tactile sensor sort of starts providing feedback. Another approach we sort of looked at, kind of building off of this, was uh, can we instead just use real world sensors as a sort of extra observation to provide guidance, and take sort of these sim to real policies, and instead of kind of merging or blending the simulation encoder with the new encoder, could we just train a new encoder that directly kind of overwrites and learns on top of kind of the original sim encoder? And so this work led by Rosie and Akash was released recently, called PTLD, which essentially kind of uses a privileged instrumented cell to collect like a few demonstrations and then fine tune on top of a privileged encoder that you get from simulation. And what we find is pretty similar, like, proprioceptive policies, uh, uh, transferred sim to real, still lack robustness. As you can see in this example, like the bottle keeps sort of going up, which is pretty common in like these rotation policies, like either the object kind of goes up or kind of falls down. And with this tactile encoder kind of adaptation through this distillation process, you're able to sort of bring back the robustness and close the loop with tactile. Use some more examples of like more objects doing rotation on the left too, and then on the right there is a kind of full in-hand reorientation as well. These QR codes are essentially used to sort of provide the goal to the policy, as there is no other mechanism to provide kind of a pose a specific goal for the object. And we also compared kind of the two approaches. So like the previous one that I mentioned, which is adaptation through blending, and then the kind of this approach, which is the through distillation. And we, in at least in like a narrow set of experiments with the in-hand rotation, we do find that Using privileged sensors does help provide extra kind of more robust information to adapt with the tactile sensors in a better way. So that leads to policies that kind of outperform just the pure kind of blending adaptation. And then, of course, we've mostly been talking about how we take the sim policies that never see tactile, and then we only have tactile in the real world. But while the progress in tactile simulation has been kind of slow, I'm starting to get more optimistic. This was a paper led by An and Jaejun that was presented at this RSS. The one of the most difficult things with tactile simulation has been transferring shear between sim and real, right? Like the older generation of simulations have been very good at transferring normal, and in fact, that was one of the results we had used even for the neural fields work. In it was the encoders there were trained entirely sim to real, but because of the geometric nature of the problem we were looking at, it was fine and we could get away without necessarily having shear be pretty good sim to real. But as you can imagine, with like these extrinsic type of contact interaction tasks where you not just care about the object in your hand but also how the object interacts with the environment, you do feel that shear in your fingers and you want to have that transfer better. So I think as a community, we're starting to kind of make more progress in tactile simulation, and I'm kind of more optimistic that this will sort of keep improving. Like for dexterous hands, I think the next thing we're looking at essentially is like how to do these with like curved sensors, and how to kind of go beyond sort of these like dot marker based gel side like sensors, but also sort of skin sensors that maybe are like capacitive or kind of magnetic kind. Essentially, like what is the kind of more common paradigm that could kind of result in better shear simulation for tactile in general. So I just to summarize, basically, I sort of see roughly like four buckets of directions where we can kind of use tactile in policies. There's the direct BC and then the two adaptation methods. And I think I'm kind of starting to get more bullish on tactile simulation. With that, I can conclude here, and I'm happy to take more questions.
All right, we have time for about 7 minutes of questions. If anybody would like to ask anything.
Can people online ask questions?
They should be able to raise their hand, and I will unmute them.
Well, I have a question already. So yeah, nice talk. I wonder. So you mentioned that you become more bullish on tactile simulation, and you mentioned it's really tricky to simulate shear force for tactile sensors. Is that the only problem though? I feel like tactile simulation is just difficult in general. What do you think, or do you think like it's already at a good state? There are only like a few things that we need to have breakthrough on.
Yeah, I think that's a good question. Just to unpack that, I think, I'm sort of putting shear as sort of the big
Mm.
villain. I feel like that's kind of more of the end result, but it's more a systems level problem to kind of make tactile simulation useful. Can we do all kinds of different morphologies? Can we make them fast enough that it can actually be easy to parallelize and uh, used within RL training, because that's kind of the more common use case that's sort of like packed into that same kind of problem. And I think the other sort of meta level question is also, once you have sort of this Cambrian explosion of different kinds of sensors, right? Like the magnetic and capacitive and image based, like what do we care about simulating maybe also becomes a difficult question, right? Because I think we can get there in terms of simulating the physics, and we can maybe get like a grid of 6DoF values for like forces and torques across kind of fingers.
Mhm.
That seems doable, I think, where simulation and kind of the state of the art is today. But I think that's different than being able to get like the raw magnetic flux for a magnetic sensor or like the capacitive change, right? Like
Mm.
I don't know if people are actually working on like how you would simulate those things, and if policies need to learn to use the direct raw sensor information, that seems like a more difficult road ahead. So I
Yeah.
think the compromise is gonna be that with real sensors, we just sort of learn some sort of calibration in the real world and, use something like Sparsh or whatever with like a little bit of label
Mm.
data and actually train models that regress to forces and torques at some discrete grid. And then in simulation, we directly train policies on those representations. And I think that's maybe one compromise. So I
Yeah.
think just directly using raw information, while quite powerful, still seems like much further away.
Thank you.
Any other questions?
I don't have a question, but I look forward. I see that this is recording. This Zoom is being recorded, and I'm pretty sure there's a couple of students at Stanford that would be interested in seeing your talk, Mukadam.
Yeah, awesome. Yeah. Feel free to reach out if you have more questions. Yeah.
I have a question. Yeah, thank you for the talk. In your opinion, what's the biggest bottleneck for achieving text manipulation? Like, if you had all the data in the world, would it still be the sensors or the actual model architecture, or is it a data problem? What do you think?
Yeah, that's $1 million question. Uh, uh, Let me put it this way. I think data is definitely going to be an important ingredient, but I don't think it's the sufficient ingredient. It's necessary, but not sufficient. Um, I think what's missing is kind of a recipe that ties different sources of information together because they're not made equal. They're kind of giving you different information about what it takes to be dexterous, right? Like human data provides something very different than the low level kind of contact rich physics that, for better or worse, the only way to get it now is simulation, right? There's no way to teleop, there's no way to collect robot data that is actually super dexterous. So I think there is a gap to be closed kind of between those two things. And I think I'm optimistic about the whole wave of like wearable devices. In fact, one just came out today. And I'm seeing sort of the convergence if you look at like the spectrum of, pure gloves all the way to like exoskeleton. I think the sort of the line between those things is getting blurred. And if we start getting more wearable devices that basically have zero embodiment gap between the device and the robot hand, I think that that's another place where we can start collecting a lot more data that's, interaction rich, but then also gives you like forces and contact and those kinds of information beyond just visual information.
We have one question online that I want to make sure that we ask from Edward Capiello. How is synchronization handled between tactile data, visual data, and proportion data? Is there a
Yeah.
limitation in this regard?
Yeah, I wish as a community, in terms of robot learning, we were thinking about this more actively. I think a lot of the focus these days is on VLA, which in that world it seems fine if you just downsample everything to kind of the same time step where vision, proprioception, all of those are sampled at the same kind of small history and same resolution. But I think as you go down the stack and you want to do high speed control, all these different kinds of tactile modalities. In fact, what we did with Sparsh X as well with the Digit 360 sensor does require to rethink, data collection in terms of ingesting different multimodal sensors at various native frequencies, right? Like contact audio is going to be a very different frequency than images, very different frequency with like IMUs. But while data collection seems plausible, it is far trickier to figure out a training paradigm that is natively allowing you to ingest and train models with multimodal kind of asynchronous multi-rate information as well, right? Like one of the kind of most commonly used libraries today is like Lee Robot that a lot of people use, and that that and kind of other kinds of these like libraries mostly make the assumption that everything is synchronized and like single rate data. So I think we should be as a community thinking about tools that are going to allow us to do asynchronous training, because that's going to be super important in terms of multimodal kind of high frequency control sort of models.
We have one last question.
Hi, yeah, thanks for the talk. My question is, we're seeing mostly tactile fingertips. What sort of tasks do you think we can unlock with fingertips? And do you think there are tasks for which we would need maybe fully textile deformable hands?
Yeah, I go back to the kind of same idea where the further the contacts are that you're trying to control away from the hand, the better you would be by having richer sensing information. Uh, so I think in general, I think, having tactile information on your phalanges or palm is definitely useful, and a lot of robot hands are trying to add that today. I don't think we necessarily understand fully beyond maybe a couple of papers at what resolution they are. Like if you just look at human hands, they are definitely denser at the fingertips than they are at the palm, for example. But we also have sensing everywhere else, right? Like we have sensing on the back, sensing on the sides that helps us do sort of these things called ulnar grasp, where you can pick up multiple different things between fingers. Or do things in clutter by feeling things in your back of your hand, like picking out keys from your pocket or something like that. So I do feel like you do need sensing coverage more than resolution at this moment.
All right, let's give a round of applause again for Mustafa.
All right. Thank you.
And now we're going to have Mark Cutkosky present. If you want to share your screen, Mark.
Yes.
Mark is a Fletcher Jones professor in the School of Engineering at Stanford University and thinks a lot about the design and control of robotic hands, including tactile sensors. And I'm sure we're going to have very interesting discussion today. Take it away, Mark, when you're ready.
All right, everybody. By the way, can you see my slide screen?
Yeah.
Okay, it's a pleasure to talk with you. I wish I could be there in person, but among other things, I've been on jury duty all week, and so I'm not able to travel. But it is a pleasure to talk with you nonetheless about tactile sensing, something that I've been interested in now for, well, over 35 years. And I, with no exaggeration, believe that more progress is being made in tactile sensing within the last few years than in the previous 20. And it's partly an evolution of technology and partly machine learning and multimodal learning. It's interesting. A lot of what's going on is what I would call tactile servoing. And that's important, but it's by no means the only thing we use tactile sensing for. And I'm not even sure it's the major one. In fact, almost nothing that I say today is going to involve tactile servoing. So my point is going to start out with the idea that tactile sensing is, people talk about bringing tactile sensing in with vision. My point is that tactile sensing of itself is already multimodal, and I'll get to that in a few minutes. It's also fundamental. If you go to the most primitive single cell animals, like a one cell amoeba, it has to interact physically with the world. And so it has some primitive tactile sensing and response. Tactile sensing is not secondary to vision or chemical sensing. It's absolutely fundamental. Well, let's look at some other animals. For example, insects. Insects are much more sophisticated than a one-cell amoeba, but they have a hard exoskeleton, like a lot of our robots do. So they don't have soft cutaneous tactile sensing. What they have are slit sensillae. You could think of them a little bit like strain gauge rosettes. They're measuring strains in the exoskeleton, and by having multiple of them, they can also tell where contact occurs. They're also dynamic. So a scorpion, by putting its legs on the ground and looking at the timing differences of Rayleigh waves as they travel over the surface of the ground, the scorpion can locate where prey is in order to eat it. The spiders actually use the same thing by looking at timing differences between different legs. They can tell where prey is in the web. And they also have other additional hair sensors for immediate contact location. But the point here is that if the goal is to do tactile sensing, there are multiple ways to do it, and it doesn't have to be a soft multitaxal kind of sensor. All right. Well, I'm a bit of a disadvantage on this talk because I'm not there in the room with you, but I think I saw briefly during one of the questions that you're sitting on chairs that have a black seat and that looks like they have metal legs. I hope that's right. And so I'd like you to do a small hands-on exercise. Take your hand and place it on the seat part of your chair. Now, I believe also that the legs of the chairs are metal. Now put your hand on the metal. You know immediately that it's metal. How do you know that? Well, feels cooler, but it's not cooler. They're all at the same room temperature. So it's worth thinking a little bit about why does it feel cooler? And this is actually a very important part of tactile sensing. It's a big part of how we identify materials. I'll get more into it in a minute. So I said that tactile sensing is already of itself multimodal. And here's a very nice slide adapted from some work by Roland Johansson years ago. And what we see here is that human tactile sensing, mainly in the hands, is already four different kinds of sensors. So we have FA1, FA sensors, and SA1. These FA means fast acting, SA means slow acting. And then 1 and 2 is whether they're superficial or deep. So the FA1 sensors, and by the way, I hope people can see my cursor here. If you can't, let me know. The FA1 sensors are up near the surface of the skin. That means they have a relatively small receptive field, and they mainly sense things in a relatively low frequency range. So if you press your finger on the corner of your chair and you hold it there, you will feel that corner for as long as you hold your finger there. In contrast, the SA1 sensors, which are also up near the surface of the skin, the Merkel endings, they're slow act. Oh, I'm sorry. So the FA1s are the faster ones, and the SA1s, sorry, are the slower ones. And yes, it's the FA1s that have this dynamic response, 5 to 60 hertz. And actually, when you put your finger on the corner of the chair, it's the Merkel endings that you're primarily stimulating. So that's the second ones here, which are the SA1s, slow acting. Okay, so we have fast and slow acting sensors right up at the surface of the skin. We also have deeper sensors. We have the Pacini corpuscles. These are FA2. These are these yellowish ones down at the bottom there. And notice that they're responsive to a fairly high frequency. I mean, 500 hertz is well into the audio frequency. And this is one reason why, if some of you are familiar with the UMI, the Universal Manipulation Interface, UMI, device, Sharan Song sometimes likes to put a contact microphone in one of the fingers of the UMI. What she's doing is using that contact microphone essentially to be a kind of Pacinian corpuscle. And then finally, there's slow-acting deep sensors, the Ruffini endings, relatively low frequency, 0 to 10 hertz, mostly measuring directional skin stretch. This means that when you load the hand, you stretch the skin, and they detect that. Again, they will continue to feel that as long as that stimulus is there. In contrast, the fast-acting ones, if you don't continue to stimulate them with an active stimulus, you won't get a signal. So they're kind of, it's like AC only. All right, so there's at least four main kinds of tactile sensing in the skin. Let's talk a little bit about how they're distributed. We have a large number. We have about 17,000 mechanoreceptors in the human hand. That sounds like an awful lot, and it is. It's actually very good. By no means the record. The record belongs to the star-nosed mole, more than 100,000 mechanoreceptors in the nose of the star-nosed mole. And at the other end of the spectrum, the worm, C. elegans, has, well, only 6 mechanoreceptors, but they're exquisitely sensitive. They'll measure 10 micronewtons of force. So if you're a worm, that's enough, but those are the kind of force levels that you need to respond to. The spacing is fairly dense at the fingertips, especially the finger pads, 140 per centimeter squared. Now, think about that for a minute. The vision-based tactile sensors that are becoming recently, they're actually exceeding these kinds of densities for those sensors. 2-point discrimination, that's if you have two little points, how close can they be together and people still feel two distinct points? And the answer is, yeah, around 1 to 2 millimeters. But actually, when there's motion going on, they can do even finer. And Roland Johansson has another paper. The answer is that they're not coupled one-to-one to nerves. So one nerve may actually reach into multiple mechanoreceptors, and one mechanoreceptor may correspond to multiple nerves. So they have overlapping fields. In any case, we can, if you give people gratings, ruled gratings with spacings down to around a millimeter, they can tell you though there's grooves down to a millimeter. If you go finer than that, they say, oh, it's texture. The dynamic sensors are a lot of how we detect really small surface features. So if you've ever tried to find the end of a roll of a piece of Scotch tape, transparent tape, it may be hard to do by vision, but you can do it with your fingers or your fingernails. You slide it over and you get that stimulus as your finger bumps over the edge. We can actually detect stimuli down to a few microns that way. Very fine bumps or scratches on an otherwise smooth surface are not hard to pick up. Interestingly, the response from these sensors is non-linear, meaning that you get a bigger difference in signal between, say, 1/10 of a Newton and 2/10 of a Newton versus, let's say, between 10 newtons and 12 newtons. And that's probably useful because, after all, at very, very light levels of touch, we really want, it's more important to know the difference between 1 or 2/10 of a Newton or 0 newtons. And then once things start to saturate, it's large. We don't need to know the details quite so much. Also interesting, however, if you have people do human subjects tests and you give them different force levels and you ask them to rank them on a Likert scale, they are pretty good at ranking them in an almost linear way, which means that our neural system is taking this nonlinear response and linearizing it. I talked about temperature a minute ago, and I hope you put your finger on your chair. What are we sensing? We sense actually both temperature and, more importantly, variation in temperature. The reason why the metal of your chair feels cool, it's not that it is cool, it's that you are warm. And so the metal is conducting the heat out of your hand faster than the seat part of the chair. And this is a very important part of how we determine materials, whether something's made of wood or plastic, or whether, for example, fabric is wet or dry. And I would say that this mode of sensing, although it's not unheard of in robotics, it's still very underappreciated, especially given how important it is in our daily lives. We also, when exploring for things like texture, use stereotypical exploratory procedures. And again, there's been a bit of this in robotics, but maybe, I think, not enough. For example, when you do surveys across groups or populations of people, we have stereotypical ways that we detect texture, hardness, softness, and so forth. And this is something that has been taken advantage of a little bit in robotics, but not a great deal. Let's get back to those dynamic sensors again. So I mentioned that the Pacinian corpuscles, they go up to 500 hertz. they actually have a peak sensitivity around 250 hertz, at which we can actually measure little bumps and things, little amplitudes down to just a few microns. And there's a good reason for that. Why would you want a sensor that's sensitive in that range? Well, let's look what happens if you're sliding over a surface. So here I've made a very idealized surface. I'm going to assume that the surface has a little bit of roughness, and I'm going to approximate it with a sine wave. And if the sine wave is kind of the way I drew it here, then the wavelength of this sine wave is approximately 4 times the amplitude. So lambda is 4y. Now we're moving at some speed. Let's say we're doing one of those exploratory procedures that we saw back here. Okay. And if I have a given wavelength and I'm moving at a certain speed, I can convert that to frequency, how fast I'm going over the bumps. So omega. And finally, if I look at the acceleration in the vertical direction, it's y double dot goes as omega squared times the amplitude. Okay, let's plug some little numbers into a spreadsheet. Let's say the amplitude is around 40 microns, which is about the thickness of electrical tape. Let's say we're moving at a modest speed, maybe 5 centimeters per second, 1001, 5 centimeters. And let's say our wavelength is 4 times the amplitude. Well, if you then crunch the numbers, you get the frequency, the acceleration, and oh my gosh, look at that acceleration. It's on the order of almost 7 Gs. Well, no wonder the Pacinian corpuscles can pick it up. So this idea that dynamic sensing could be important has not escaped people. I mentioned I've been working on tactile sensing for something like 35 years. Here's a paper with in fact, my very first PhD student, Rob Howe, who's now at Harvard, using little piezoelectric strips and a little miniature accelerometer as a kind of a crude approximation to a Pacinian corpuscle on a robot finger. And we were doing some work with, in fact, Roland Johansson's guys. And the setup here on the left is some data they took. What they had subjects do is hold a block of wood, and concealed inside that block was a little solenoid. So you'd pick up the block and you'd lift it, and then at some point the solenoid would fire and you'd get a little jostle. And what that does actually is it triggers an unconscious response that the user interprets it as incipient slippage, that they're in danger of dropping the object. So they increase the grasp force. And the plot's a little hard to read. Remember, this is old. This is from 1993. But what you can see is that the normal force, the grasp force they're applying, it goes up as they lift the block, and then this is classic. People are lazy, the grasp force decays with a kind of exponential decay, and then that little jostle happens and the grasp force updates, and it stays that way for a while, and then it will start to decay again. What's a couple interesting things here? One is that the adjustment's fast. 80 milliseconds is very fast by biological standards. It means it really is a reflex. Secondly, the interesting thing is that people did not habituate. It worked reliably every time. And in fact, afterwards, when they interviewed the subjects, they said, yeah, that object was kind of weird. It was weirdly slippery. And I kept having to readjust my grasp. Going a little further, we can think one of the things that becomes clear is that these different mechanoreceptors, the fast and slow acting, the superficial and the deep, one of the ways we use them is to follow the progress of a task and determine whether the task is proceeding normally, and also to distinguish between one phase and another phase. So here is a task of grasping something like a coffee mug and picking it up from the table and holding it, and then putting it back down again and releasing it. And so when your fingers first make contact with the mug, the superficial sensors, those are the FA1, SA1 right up there on the skin, they fire quite a bit. And notice, by the way, that the fast-acting ones fire right away when you make contact, but then they kind of stop firing, whereas the slow-acting ones continue to fire. Then, as you lift the mug off the table, well, it's impossible to lift that mug without it scratching or bobbling just a little bit off the table surface. And so you get a dynamic signal from the FA2s, the Pacinian corpuscles. And this, by the way, is also what the contact microphone on the UMI would notice this as well. And now you hold it, and not a lot happens. We get steady firing from the grasp force and from the shear forces in the skin. We were talking about shear forces earlier. And then as you put it down on the table, once again, you get a bunch of spikes from the Pacinian corpuscles due to that impact. And finally, your superficial sensors fire as you release. So this is interesting. And I thought it was especially interesting when I compared it to how not a lot of people, but some people are starting to use multimodal sensing in robotics. So here's a paper from a few years ago by Hao Li, who, by the way, just defended successfully his PhD this morning. But this is some older work he did for his master's, where he was looking at touch from the gel site tactile sensor, from audio, which he converted into a spectrogram, and then from vision. So actually, in some sense, I would say he's cheating a little bit here because he's converted everything into an image. He has vision image, he has audio, which he's turned into an image, and he has gel site, which is also an image. But the point I want to make is not that. The point I want to make is look what happens. So this is a task, this particular one has to do with sticking something inside a box where you lose sight of it as it gets behind the flaps of the box, and you start having to rely on contact, on touch and sound. And so we start out, and vision's very important. And then as we get to where it's starting to be occluded, of course, vision becomes less important. And then touch and audio get much more important for a while. And then as you withdraw, vision gets more important. And what's interesting is that looking at when the relative attention score for one of these modalities is changing, like here and like here and like here, is, I think, kind of similar to the way that we see in biology um, the roles of different types of tactile sensors are becoming more or less important. So interesting thought. Okay, so where are we? Well, like everybody else, we're using combinations of different tactile sensing. Yes, we use visual-based tactile sensing. We also combine it with our COIN-FT, our little tiny six-axis force torque sensor, which we've released as an open source design. And it's kind of interesting to think about when are these different types of information useful? So I've color coded it a bit. The pink ones are slow, so you could think of those as the slow acting sensors. I include vision there because we're only grabbing the vision at 30 frames a second. Useful for contact patch size and location, tracking the centroid. Also, it gives us a lot of interesting information about the physical texture, for example, of the strawberry. Using a combination of COIN-FT and imaging, we also can say something about how the contact pressure is changing as we manipulate the strawberry. And then finally, the COIN-FT, although it's not super fast, it's 370 hertz. It is, however, fast enough for us to detect things like incipient slippage and the bobbling that occurs as you pick up a tool or put it down and so on. And so in manipulation, what do we use that for? Well, again, color coding. The slower things, I think, have to do with object identification and slow tactile exploration. The medium fast things have to do with what I call tactile servoing. And finally, the fast response for things like slip control are on the bottom. I want to bring back up one other thing, which I think is fun. I've put a QR code, and the URL is here. And in fact, at the end of the talk, I'll paste this URL. Whoops, paste this URL into the chat window because it was never published as an article, but it's been out there for a while, and a number of people found it useful. And in fact, I'm just going to pop over there for a minute. Yeah, okay, it's old. What happened in 1995, Mike Costa, who was a PhD student and a researcher at NASA, and we found a newspaper article about a professor of paleontology at University of California, Davis. And he had just won an award because he had realized that some of his colleagues had misidentified a certain kind of fossil and he had identified it correctly. And the reason why is that he's blind. And he had explored these fossils entirely by the sense of touch, and he was not fooled. He was not influenced by visual cues that turned out to be incorrect visual cues. And so we thought that was fascinating. And we drove over to Davis and we did an interview with him. And this article online is about that interview. And there were interesting themes that came up, multiple scales of time and space. So one of the interesting things is we asked him, you must, of the arts, you must really appreciate sculpture. And he thought for a while and he said, well, the thing is, I really only appreciate small sculpture because large sculpture, I have difficulty integrating spatially. Um, Small things that I can get my hands around, yes, I appreciate very much. He talked about how he sensed large features and fine features. For really fine features, he gives himself a stylus. He uses a hypodermic needle, and with his fingers, he uses it to trace the contours of fine features of fossils. We talked about effects of cold. Cold is interesting. It anesthetizes. Oh, we talked about how thermal sensing is important for materials, detecting materials. Cold also, unfortunately, anesthetizes the tactile sensors. And so your fingers get numb when you're cold, and it's because your tactile sensing's gone. So when he did work underseas, he would wear gloves, but he would still cut the fingertips off because he needed that tactile sensing. And a few other things. And so I'm not going to belabor it now, but it's some interesting points. All right, so where are we now? One of the things that we have really become interested in is tactile sensing for underwater manipulation. I think for us, it's the next frontier. There's been so much amazing progress in tactile sensors. I think a new one comes out every month, and they're getting better and better, and people are finding better ways of using them uh, in robotic manufacturing and other tasks. This one is still pretty unmet challenge. And one of the big challenges, of course, is that you're at 1,000 meters down in the ocean. It's 1 atmosphere for every 10 meters, roughly. So we're talking 100 atmospheres and more. That absolutely rules out many tactile sensing technologies. Also, you're in salt water, which is corrosive and highly conductive and has a high dielectric constant. So given all that, what are we looking at? Well, there is one technology that works well. It's optical fibers with Bragg gratings. These are used in the gas and oil industry, and you can build them into fingers and fingertips. And so that's what we've been starting to do. There's one paper that came out in IROS last year, but we're actually working on some new tactile sensing ideas. And I can talk about that in the Q&A if people are interested. And that, I think, wraps it up. Because I do want to, if there's time for a question or two, I'll take it. Thank you all.
Are there any questions? Any questions in the room or on? There seems to be one person with a hand raised. Molong.
Let me go ahead and put that URL in the chat window.
Hey, Mark, can you hear me?
Yep.
So very nice talk. So I have a question regarding the last bit. You mentioned you want to use the FPG sensor to basically use as a tactile sensing. We have used those type of sensors in like flexible aircraft aeroelastic reconstruction
Yes.
field. But one major bottleneck or limitation I see from usage in the like tactile sensing is that the demodulator or the other equipment
Yep,
may
the
be too large.
interrogator.
Yeah. So do you have any like way to bypass this issue? We have several different
Yeah.
ones. We have larger ones, we have smaller ones, but the smallest one we can get is about larger than the computer size. So I'm not
Right.
sure your like a vision
Well,
on.
they are getting smaller. It's not, I mean, the smallest ones now are the size of I don't know, a CD player that you'd plug into your laptop. Uh, that's not too big to put on the backpack of Ocean One. And also we actually, this is interesting because we have another smaller robot, and we found a couple of optical interrogators that can go into sleep mode, but even when they're running, they're only using about 5 watts. So that looks promising. And but the other thing, if for initial experiments, most of the time when we're running Ocean One, it has an optical fiber tether up to the boat anyway. And one of the nice things about FPGs is that the interrogator can be up to a kilometer away. I don't think that's the long-term solution, but in the short term, we can leave the interrogator on the boat if it comes to that.
I see, I see, I see. That's quite smart. Okay. Yeah,
Yeah.
so we are
On
also
a drone,
working
though, you
on,
have a harder problem because your weight budget. I don't know how
yeah,
big your
yeah.
drones are, but the drones that I've worked with for perching, yeah, there's no way I could put an optical interrogator on them.
Right, right, right. So we're also working on like a manufacturing methods to basically 3D printing this together with other structural parts so that it's more integrated. Yeah.
Hmm.
Okay, thanks a lot for the information. Yeah.
There's one question in the room. Hey, thanks for the great talk. I think it seems to me one of the big reasons that Visuo-Tactile sensing has been really popular in the robot learning world has been because we can use, something that is akin to an RGB type data standard and have rectangular images for everything. I'm wondering, for some of these other types of subcutaneous tactile sensors, things that can't really right now be represented in that kind of way, do you think the bottleneck to integrating them is the data representation, or is it something to do with the density of the sensors themselves?
I think it is partly, well, I think it's both of those. There are efforts to do multimodal fusion, treating the dynamic sensing. I mean, it's in some ways it's more close to how people are starting to fuse audio with vision. And you do have to respect the fact that you're pulling in data at a fundamentally different rate. You do have to timestamp. I don't think you want to just downsample, to to match your vision, because then you lose these, the salience of these important tactile events. Um, but it is a fundamental thing, and you know this because if you watch a video conference and the connection is not great, you tolerate choppy video much better than you tolerate choppy audio. And it's really the same. Tactile sensing in that regard is much more like audio.
Yeah, awesome. Thank you.
All right, we have time for one more question if anybody has. Okay.
Hi, Mark. Thanks a lot for the talk. A
Hi.
lot for thought in there. I'm wondering, if you have any thoughts on, as you're saying, we have lots of new tactile sensors with fantastic performance. But a lot of that is performance, on the spot, in one moment. Where we're still falling short is sensors that can stay at that level for days and weeks and months, and the signal doesn't change, right? And also the sensors that don't have a change in performance, either on very short time scales or very long time scale, right? We can pick up a 60-pound suitcase and then put it down, and then 2 seconds later find the end of the scotch tape. And then, week after week, year after year, our tactile sensors work the same, but in robotics, performance degrades right away, and you have short-term hysteresis, long-term hysteresis. Do you have any thoughts on how we can build sensors that just work the same way forever, essentially?
Yeah, I mean, I completely agree with you. It's a problem. I mean, a few thoughts. One is that tactile sensors have a hard life compared to vision. The vision, you got a little CMOS chip behind a lens. It's separated from the world. The only thing it has to deal with is photons. Tactile sensing's out there on the skin, scraping and rubbing and banging into things. I mean, yeah, it's hard. The thing about being the same, I mean, I mean, it's getting better, but it's also the case that we may need to learn better how to sort of continuously dynamically recalibrate, because actually your hands and my hands, when they're cold, their sensing properties are quite different, and we learn to deal with that. Or if you've actually been holding on to something which is vibrating for a while, it profoundly changes the characteristics of your tactile sensors for a while, and you learn to deal with that. And I feel like maybe, okay, so, maybe the robot tactile sensors will vary somewhat over time as a function of temperature, for sure. Um, but if they're doing repeated tasks where we kind of know that the answer should be the same as it was yesterday, maybe robots like us, like animals, should get better at sort of continuously dynamically recalibrating. Um, and we're not there yet. Yeah, I mean, I agree with you. It's a problem.
Thank you.
All right, let's thank Mark one more time.
All right.
Zinan, if you want to take us away.
Yeah, sure. Can you see the screen, right?
Yes.
Yeah. Hi everyone. I'm Zinan Li from USC. Today I'll present Felt, a framework that generates tactile signal directly from vision. Our goal is to recover the benefits of touch for context-rich manipulation while reducing the need for visual tactile data collection. Touch is especially valuable when vision is occluded or ambiguous. However, tactile data is much harder to scale up than visual data because sensors are specialized, fragile, and difficult to standardize. Meanwhile, many large robot datasets contain only RGB observations. This creates a major data bottleneck for visual tactile policy learning. Our key insight is that when the gripper object and the contact region are visible, RGB already provides strong clues about where and how contact happens. Felt learned this mapping from existing pair visual tactile data. And once trained, it generates per-finger tactile observations from a single RGB frame and provides either tactile images or latent tactile features to downstream policies. Felt use a frozen Dino V2 encoder to extract visual tokens. And because the two finger sensors are separate surfaces, we decode them with two position-aware query branches that match the 12 by 32 sensor grids. A gated exchange module coordinates the branches while preserving asymmetric contact. Finally, a panel-aware convolution hair predict contact probability and pressure intensity, and its intermediate feature can also be passed directly to the policy. Here are qualitative prediction on our test dataset. Compared with mask autoencoder, Felt better recovers both contact location and pressure magnitude. The ablation shows why the topology-aware design matters. Removing the dual branch or convolutional head underestimate the contact, while removing the panel exchange produce incorrect left-right force balance. Quantitatively, Felt also achieved the best perceptual similarity and total pressure calibration. We evaluate Felt on 4 contact-rich tasks: tube insertion, cup nesting, eraser wiping, and triangle pack insertion. We collect 60 demonstrations per task and train separate diffusion policies. This clip shows the 4 tasks with generated left and right tactile signals below each RGB frame. Each method is evaluated for 20 real robot trials per task. Real tactile consistently improves over the vision-only method. Replacing the sensor at deployment with Felt-generated tactile also improves final success across all 4 tasks. Matching real tactile on cup nesting and triangle pack insertion task. Felt features use no real tactile readings during downstream policy training or deployment, yet remain competitive with real tactile and reach 90% on triangle pack insertion task. To summarize, To summarize, felt generates structured per finger tactile signal from a single RGB frame using a topology-aware architecture. Both generated tactile images and latent features improves context-rich manipulation task over vision alone, enabling downstream policy without physical tactile sensors at deployment. And thank you. I'm happy to take any questions.
Right, we have a minute for questions. Are there any questions from the audience? All right. Do you have a question?
Hi. Thanks. Thank you for the great talk. I have a question. How your method would work for for example, sleep detection, where vision can't really see the interaction between the object and the hand?
Our method is mainly focused on the big tactile image change, like the rotation and reorientation. For the sleep detection or the small vibration, we are still working on that, and it's really hard to tell the difference between the sleep or not from the vision alone. Yes, thanks for asking.
Makes sense. Thanks.
Okay. Thank you very much, Zinan, for presenting.
All right.
Next, can Kelin start presenting your screen?
Yeah, can you guys hear me now?
Yes, we can.
Yeah, sure. All right. So, yeah, hello guys. It's Kelin. I'm from UMD. So today let's talk about our project, the OmniTacTune, Policy-Agnostic Real RL for tactile residual adaptation. Start from the beginning. I want to highlight that we already have huge amount of visual data can be used for large-scale visual policy pre-training, but that's not enough. So it's hard for us to scale up tactile data for context-rich manipulations because we have different kinds of tactile sensors, and for different tactile samples, the performance is also different, and there are a lot of different contact variants. And here are some reasons we utilize specific hardware like Tactile Wumi or using the tactile simulator to scaling up tactile data. However, they cannot leverage abundant visual data which are already variable. How can we enable that? So our idea is that we can have the pre-trained visual policy and we adapt the tactile feedback via the real-world interactions and using the tactile feedback to adapt to the base policy. And it's inspired from the human experts. So here is a demo for the kendama. So we have a lot of expert demos from the YouTube videos. But just watching them is not enough. Humans still need to do in practice with our tactile feedback and the perceptions. And we choose to use the residual policy. The first thing is that it will not change the base policy, and also it can enable the fast and close-loop corrections to the base action trunking from the base policy. And we choose the real-world reinforcement learning because it has large central gap for the visual tactile sensor. And it's also hard for us to simulate all the objects and the real-world dynamics. So we propose OmniTacTune. First, we have various different base policies, and we fine-tune it with the OmniTacTune, and evaluate in 4 different context-rich manipulation tasks. So in the first step, we collect both human video plus retargeting data and VR teleported data to train different kinds of base policies. And that is the most important part. We have a 2-stage real-world tactile residual RL pipeline. In the first stage, since we don't have the visual tactile expert demo, we're just doing the one star to initialize both the replay buffer and the critic, and also fine-tune the tactile encoder. In the second stage, we train the tactile residual policy. Why our policy can be policy agnostic to the base policy. So we have the object-centric flow as the cross interface. It can both for formulating the flow tactile residual policy and the policy independent reward. And also here is a demo for the generated object-centric flow. And for the dance reward shaping with the generated flow, we can do in matching with the robot flow to formulate the dance reward, and also using the tactile grasping reward and the tactile slippery penalty to build our reward shaping pipeline. So for the residual policy, we use both the flow input and the action trunk from different base policy to enable the policy-agnostic adaptation. And we're also using the contact gate to the tactile input to increasing the tactile efficiency. And we conduct experiments in 4 contact-rich manipulation tests, including the pegging hole with spatial generalization, the precise charger insertion, and to using tests for cap opening and the contact-rich box opening. And so we compare it with different RL pipeline to show that with this formulation, our pipeline with Von Star and the general policy is more efficient. And we show that it can be generalized across different data sources, different base policy like human policy and Pi 0.5, and different tactile representations like different tactile encoders for tactile images and the tactile mask. And we show that within 1 hour training, so it can increase 50% success rate for all of them. And we also conduct evaluations for reward shaping, residual policy, Von Star strategy, and the action space design. And finally, here is a 1-take 40 minutes training demo to show its effectiveness. And I'm here to take any questions right now.
All right. Are there any questions? Anybody have any questions for? All right. Let's thank Kelin for a great talk.
All right, thanks for listening, and here are more details about our projects, and thank you, everyone.
All right. Would Qing please share your screen?
Okay. Hello, everyone. I'm Yunzhu from Tsinghua University and touching text. Today, I will present Tac-Cerebellum, a lightweight multimodal reflex policy for context-rich robotic manipulation. Large vision language action model supports semantic reasoning, but context can change faster than they react. Tac-Cerebellum therefore provides fast local control through selective tactile encoding, adaptive cross-modal modulation, and efficient action generation. Why do we need fast tackle reflexes? Vision cannot reliably reveal contact area or force distribution, especially for reflective, transparent, occluded, or fragile objects. Touch is useful only when it is fast. In contact-rich tasks, delayed feedback becomes post-hoc diagnosis rather than closed-loop control. Our goal is to encode tactile dynamics, fuse modalities adaptively, and generate actions with low latency. We built a multimodal system with flexible electronic skin on both gripper pads. Each pad contains a 32 by 58 tactile array. Together, they form a 64 by 58 map with 1.18 millimeters resolution at 40 Hz. Touch, vision, and robot proprioception are synchronized for real-time reflex control. Tac-Cerebellum has 3 modules. First, member equals fast tactile streams, suppressing redundant free space history while retaining important contact transitions with linear complexity. Second, build grounds each modality using the other modality and robot state, while swing glue routes state-critical channels. This provides 2 benefits: intermodal balancing draining contact and intramodal refinement that preserves stage-critical features. Finally, in vital state action generation, The fused multimodal latent directly serves as the flow source, avoiding Gaussian initialization and repeated sensory conditioning. We then evaluate disturbance rejection and safer contact response. When the cylinder is manually rotated, the vision-only baseline falls under partial occlusion. Tac-Cerebellum detects the tactile change and compensates. During misaligned insertion, the baseline keeps pressing downward, while Tac-Cerebellum detects asymmetric resistance and performs a complex rollback. High-frequency touch therefore supports online correction and safer interaction. Finally, we test re-engagement under pose shifts. After one replacement cycle, we move the objects drawn in continuous inference without recalibration. The vision-only vector baseline falls because its visual feature allocation remains too static. Tac-Cerebellum reweights visual and tactile features, regauges, and completes the text again. Current limitations are insufficient analysis of tactile features and model selectivity in limit tasks and modest tactile games. Next, we will refine tactile representations, improve fusion, explain text, and release the multimodal data. Thank you.
Are there any questions for the author? If there are no questions, I have one question about you used a Mamba layer instead of something else. Was there a particular strategic reason why that was chosen as the architecture?
Yes, I think compared with the CNN, Mamba is less limited by fixed local patterns, and compared with the transformer, it can avoid quadratic attention cost. I think it's very suitable for the sparse tactile data.
Excellent. Thank you so much.
Okay.
All right. Our next speaker is Jianxin Li, who will be presenting Heterogeneous Tactile Transformer. Just feel free to put your computer right here. Are you sure? And you have to share your screen. Yeah, sure. Zoom. Just hit play. Perfect.
Should I use a mic or not?
You can, yes, use the microphone, please.
Okay. Test. Okay. First person to speak in person. Okay. So hello everyone, I'm Jianxin from the Peer Lab at NUS. Glad to be here to present our work on heterogeneous tactile transformer. Tactile sensing is important for contact-rich manipulation, while tactile sensors are heterogeneous and they are evolving faster. One model trained on one tactile sensor can barely transfer to another sensor, which means that every time when we have a new sensor, we have to recollect our data and retrain our model. So a question we are facing is how to leverage heterogeneous tactile data for representation learning and policy learning. In HDT, we propose first a scalable approach to collect heterogeneous tactile data in pair, and also a self-supervised learning method to learn shared representation from such paired data. We first talk about how we collect our data in pair. We use a uni-style graph pair with two distinct tactile sensors mounted on each side of the graph pair and interact with the objects. One interact with the objects, two tactile sensors, they are collecting spatially and temporally aligned tactile signals. This forms our paired perceiving data. And to evaluate model performance, we also collect labeled perception task data, including object classification using the UMI device, and also using FT sensors to help us get 3D false from truth for false estimation tasks, and also slip detection tasks. In total, you get around 1.6 million frames of tactile data in one dataset, spanning for 4 different tactile sensors, including both optical-based and texel-based. Now let me introduce the heterogeneous tactile transformer. So with paired data, the heterogeneous tactile transformer taking heterogeneous data, the sensor-specific encoders and a shared transformer chunk are the core modules. We introduced 2 different training objectives to fuse the sensor presentation. The first is the master reconstruction through an MAE-style reconstruction objective. Each sensor is, the model is trying to reconstruct the model input within each modality. But with such an objective, the model cannot align different sensor embeddings. So we further introduced the cross-modality alignment. For paired tactile data, we use one sensor embedding to predict another sensor embedding through the cross-modality predictors in the latent space. The benefit is that since the data are paired, they share similar content information, and prediction in the latent space allowed the post model to encode similar content information into the embedding space, and this aligned the tactile representation from different modalities. With training on the HPT data cycle, our model can learn shared representation from heterogeneous tactile data. And we do further evaluation first on perception tasks, including object classification. So we compare with training from scratch and 2 other tactile models that pre-trained on large-scale optical-based tactile data. We find that our model can perform much better than theirs. And a variant of ours, which we show in MAE, is a model that pre-trained but using our model, but without using the cross-modality alignment objective. We found it performed reasonably, but not as good as our HTT, which suggests that such cross-modality alignment benefits the representation learning. And we found similar results on false estimation and sleep detection. More importantly, HTT can adapt to the unseen tactile modalities in simulation. For example, in the pack insertion and bomb installation, HTT is used to zero-shot to encode tactile RGB information or tactile force field information for policy learning. And we show that HTT can actually perform the best comparing to using other representation for policy learning. We also conduct real-world tasks, for example, in such a toy group, comparing to using a 6D force vector on fingertips. HTT actually boosts the content-rich policy learning by providing richer content information and leads to much better toy group success rate. And in another fragile grasping task, which we grasp a soft tofu, a room temperature tofu, HTT is shown to grasp the tofu gently without breaking it without slippery, comparing to using simple force vectors as the condition. So through comprehensive evaluation, we show that HTT actually improved tactile perception performance, boosts the policy learning, and adapts to unseen sensors in the real world. And to summarize, we believe that learning from paired tactile data is a promising path toward generalizable tactile representations. From the data perspective, we propose the OmniTacTile device that making such paired tactile data collection scalable. And also from the model perspective, we propose such cross-modality alignment on paired data, showing that it can further improve the heterogeneous tactile pre-training over comparing to MAE pre-training alone. Here are our paper and demos. You can scan the ticket for more details. And also welcome to talk to me. Thanks.
All right. Thank you, Jianxin. We have time for one question. Yep.
Hi, yeah, thank you. Very interesting. One question about the heterogeneous data collection. Must the object be symmetric when you collect the data, so the measurements will align?
Yes. So we use the OmniTacTile gripper, right? And the OmniTacTile gripper is symmetric. When you mount 2 distinct sensors on each side, when you make a contact with the same object, actually they are obtaining very similar contact information. I won't say identical because I can't guarantee that, but they are symmetric. So the force should be the same. The textures should also be similar. And in such a case, the contact information is actually naturally aligned when you do the data collection.
Yeah, but only if the object itself is symmetric.
Object itself is symmetric. Right. Yes, and for the force and others, those are not in the pre-training data set. Those are just for evaluation because we want to see after pre-training how the perception can be evaluated from a different perspective.
Super smart. Thanks.
Thank you.
Thank you again. And would our next speaker please start sharing your screen?
Okay, can you see my screen?
Yes.
Should I start now?
Yes, please.
Okay, thanks a lot. So it's my great pleasure to present our work. Where did I touch? Learning surface block tactile representation for single-shot contact localization. So this is a joint work by Pengfei, me from Hong Kong University of Science and Technology, and also Yuxing, Yuxiang, and also Edward from MIT, and also Honan from Harvard, and also Chuanzhi from the University of Sydney. So the reason that we are looking into this is because for a lot of manipulation tasks, we know that there might be some challenging environment where it will be difficult to access. For example, if you want to access the drawer, and also some of the human-robot collaboration tasks, you will see that human will have oscillations during the manipulation process. And also we know that some tasks, they will require dedicated orientations. For example, the insertion task, which many of the previous presenters have already discussed. For those tasks, we know that the vision will have a certain angle that we may not be able to satisfy the vision-based requirement. And also we know that for the transparent object, typically the vision-based method would be relatively limited. So that's the reason we want to bridge a gap to see if we can use the CAD model to enable the localization with the help of tactile sensing. And we also want to explore how to use this framework to incorporate into the downstream manipulation tasks. Okay, so in that regard, the simple definition we wish to achieve within this paper is to enable the system to estimate the contact location with just single one touch, and also to provide the localization input to downstream action models. Okay. So since this is a short presentation, we would like to start from a demonstration first and then gradually go deeper into the method. So in the beginning, we can see that we use a iPad type of scanning app. So this is a Kiri app, which enables the direct scanning from our mobile devices. And once we have the CAD data, either from scanned or from the original CAD data, we basically have the mesh to point process where you basically have this dense cloud. And then with this cloud, we have the partitioning so that you can have a lot of the small patches, which is basically distributed along the surfaces. And we will have smaller local tactile basically point where they will be used as basically where you have the testing data. Okay. And after you have that, we also have the experimental demonstration showing that if we have both the contact from the motion capture system with the tactile sensing and also basically a particular object. So we have a ground truth signal, and to verify the detailed localization methods. And then basically we can use that for downstream tasks. Okay. So with that highlight information, I would like to go deeper into this. So I think the first stage is relatively straightforward. We just have this basically decomposition. In the second stage, we basically have the tactile surface localization with the point cloud, with also the block information. So assume that with a real time, like a point cloud information from the tactile, we can basically establish a neural network, which basically you can have this network with a tactile encoder with surface block matching. So you know how close this current real-time measurement is mapping with your existing batches of existing information. And then you basically can have additional basically pre-trained weight and also have basically a determination module to understand what will be the final pose in this manipulation task. Okay, so in that regard, we have also a coarse-to-fine localization network, which will have visual pre-training with a patch sample dense from the mesh, and also few shots fine-tuning from a small set of the real tactile contacts. So here is the detailed network structure. You can see the input. You can see this is basically the features. We are using like a coarse candidate retrieval from a cosine symmetry encoder so that we can compare the either from the data or from our like test data how close we are from the localization of these maps. And by having a neighborhood retrieval, we basically are comparing how close it is to the neighborhood and with a shallow, small like MLP trained to predict the within block offset, and then we basically have a coordinate on top of the entire surface. So here is basically the experimental details. Here you can see on the right is the comparison from the ground truth and our methods. So these have been investigated for a long time. You can see that the previous, the iterative closest point method, ICP method, is a classical method for these purposes. And with our enhancement, we basically can significantly reduce the localization error for the manipulation. And here is basically how we are using it for like downstream manipulation task, including if you have multiple grippers or multiple contact point, how do you reconstruct the pose with more confidence, and also you know the entire pose in 6D rather than only know the localization on the object. And also here is another example we showed you earlier that with the camera occlusion, still we are able to manipulate the basically this is a hand drill model under the camera occlusion. Okay, so I will conclude my presentation here, and I welcome any questions for this work. Thank you.
Are there any questions? I'll ask one question, which is, you know, estimating contacts is very important. How do you propose that we take this further for getting better affordances for objects downstream?
Yeah, so this is essentially currently we are basically having this framework. We are only trying to do the localization for this work. But if we are trying to incorporate that into the downstream work, as I just mentioned, because currently we assume that you can have a CAD model of the things you are manipulating, so that as previous presenter has already shown, if you have a more accurate contact location, then you can do like more like the in-hand manipulation, or you can do multi-contact basically reconstruction, and you can basically to have more dedicated work so that you can use the tool to handle some more dedicated work. So that is something that we may wish to continue exploring using this localization methods.
Okay, great. Thank you very much.
Thank you.
Would Siyu Ma please start presenting?
Wait me for a second. Okay, can you see my hello everyone, my name is Siyu Ma. I'm a first-year PhD student at UCLA. Today, I'm very grateful for the opportunity to present my work at this workshop. To integrate tactile feedback into pre-trained VLA policies through simulation, we present TacCoRL, a scalable framework that combines simultaneous training with simulation-based reinforcement learning. Precise contact-rich manipulation requires both vision and touch. Vision interprets the scene, while touch reviews contact interactions. For robots, the challenges are clear. Visual ambiguity in subtle contact states, limited supervision for near-failure recovery, and the cost and risk of exploring failures directly on hardware. To address these challenges, we propose a three-stage framework. First, we collect a small set of real demonstrations and expand simulated teleoperation data with MimicGen. Then, simultaneous training injects tactile history into the vision language model backbone and action expert, giving the pre-trained vision language action model an initial tactile condition behavior. This makes sparse reward reinforcement learning tractable by turning exploration from scratch into context-aware policy refinement. Finally, IO fine-tuning uses sparse reward in simulation to learn context corrections, where real demonstrations enter the update and prevent simulator-specific drift. Our pipeline enables TacThru to adapt VIA policies with limited real data and safely refine tactile-guided behavior in simulation. To make simulation training useful on the real robot, the simulator must match how our policy sees, acts, and feels. So we rely on the task settings, cameras, controller response, and tactile readings using 128 parallel simulation environment. The policy can safely learn context recovery behaviors that are hard and difficult to collect on real hardware. Here's the representative real route for test tube insertion. Across trials, the tube starts from randomized initial pose. As the robot approaches the rack, the gripper at the tube increasingly occludes the opening, making the critical contact states difficult to infer from vision alone. Upon rim contact, TacCoRL uses tactile history to make small closed-loop translational and rotational corrections rather than pushing them directly downward. These adjustments reduce angular misalignment and enable continued insertion, allowing the policy to recover from diverse near-failure contexts and complete 4 consecutive real-world insertions in this representative route. This ablation shows that both vision and simulation fine-tuning are needed. Without touch, the policy cannot observe hidden contact errors after occlusion, so it often keeps pushing in the wrong direction. With touch but without simulation fine-tuning, the policy can receive tactile signals, but it hasn't learned how to convert tactile readings into recovery actions. Our method combines tactile feedback with simulated trial and error, allowing the policy to search, reorient, and stabilize contact before insertion. This leads to a more reliable contact-rich manipulation. We evaluate our policy on 4 real bimanual contact-rich tasks: test tube insertion, puzzle placement, and 2 assembly tasks. Across these randomized real-world trials, the final Visuo-Tactile policy achieves 72.5% average success rate. This demonstrates that tactile feedback, refined through real-line simulation, can generalize across contact-rich settings and can be effectively integrated into pre-trained VIA policies. Okay, thank you for listening. Do you have any questions?
Are there any questions in the audience? Anybody have any questions? If there are no questions, sim to real gaps can be very challenging. And it seems like you've worked very hard to reduce them as much as possible. Are there any other limitations that you're worried about in this strategy that you've chosen for some of the tactile manipulation that you're working on?
I think for considering our topic, tactile sensing for Robotic Foundation models, simulating high precision tactiles is very challenging. This is one part. And the second part is because contact-rich manipulation, very careful and comprehensive system adaptation is really needed. I think these 2 points are the 2 main challenges for contact-rich manipulation in using tactile and in the sim to real transfer domain.
Great. Thank you so much for your presentation.
Thank you.
And our last but not least presenter, Yu Young, can you please share your screen?
Cool. Can you see my screen?
Yes.
Yeah, thank you so much. So this is Yunzhu Li from Peking University in China. I'm glad to be here to share about our recent paper on fingertip integrated simultaneous tactile visual sensing for multimodal robotic manipulation. So everybody in the room might be familiar to the vision-based tactile sensors or VBTS, right? From early research from MIT to the recent commercial products, our lab has been tracking its progress, building the full duck hand with full hand tactile sensing, TacMan for peripheral articulated object manipulation with tactile, and TacCoRL, the vision-based tactile sensor simulator on GPU. So throughout our research, one key issue of tactile sensor have been bothering me. That is, they're blind until the moment of contact. Okay, so they only provide post-contact feedback, and they cannot perceive the latch inch gap near the fingertip prior to interaction, which is really vital for precise contact and manipulation. So to bridge this gap, our solution is called TacThru. It is a see-through skin sensor that provides simultaneous vision and tactile sensing from the robot's fingertips. So it's based on a VBTS design, but it removes the reflective coat so the camera inside can see through its skin, which is the transparent elastomer. So the robot now can actually see the object from its fingertip prior to the moment of contact, while also tracking the visual and tactile signals of the object and the environment throughout the entire interaction process. So the issue here for tactile sensing is that although the transparent elastomer make vision clear, it also make it tough for tracking conventional tactile markers like the black ones you see here, as they may vanish when the background is also black. So we have designed the keyline markers, producing concentric double-layered markers with high contrasted colors, so the black and white ones here, so the detectable feature will always be visible to the camera. So this is more clearly demonstrated by the comparison here. You can see the black markers easily vanish due to the dark background, while our keyline markers ensure detectability and no marker is missed. We'll also introduce a super lightweight blob filtering technique to refuse the false positives due to the blob-like patterns from the environment misdetected as markers. So finally, we can firmly track all the real markers as shown by the green arrows here. And this tracking is super effective and efficient, achieving full marker tracking with only a subtle time budget of about 6 milliseconds. So this enables high frequency runs like a 120 Hz one. And also the fabrication of TacThru is super compatible to the VBTS sensors. So if you guys can make a VBTS sensor at your lab, which I believe so, then you can try to build a TacThru sensor using exactly the same material. And before you get your hands dirty, check out our further results on manipulation through a WUMI platform performing various tasks, including picking up a thin and soft tissue, a paper tissue that tactile sensors fail to detect, and sorting tiny balls into the correct bowl that they are hard to see from the wrist camera. Hanging a pair of scissors where fast response to tactile cues is vital, and performing insertion tasks with near-field vision for visual alignment. So these tasks highlight different modalities that TacThru provides, the near-field vision and tactile sensing, all provided simultaneously from a multimodal sensor, achieving persistently superior performance over other baselines. So as a quick summary, we proposed TacThru. It is a see-through skin sensor that provides simultaneous visual and tactile perception from the fingertips. The clear elastomer ensures clear vision, and the keyline markers allows for efficient and robust tactile sensing, supporting fine-grained and contact-rich manipulation tasks. And we believe TacThru represents one of our explorations towards superhuman level capabilities, where human-like ones, they're not just enough. And we have already seen these capabilities in language and visual foundation models in terms of reading, writing, and reasoning. But the world is still waiting for the building blocks for robots and visual foundation models in achieving superhuman level perception and manipulation. And that's all I'd like to share. You can find more details on our website. And this is a quick live demo. Although I can't be there, this is a quick demo. You can see from our sensor, and you can see the visual signal and also the track tactile markers shown in the red arrows here. Sorry, I can't give a live demo there, but I'd like to listen from any open questions. Thank you so much.
We have time for one question. Are there any questions in the audience? Yeah, please.
Yeah. Hey, thank you for the talk. It makes a lot of sense that you need vision as well as over tactile, like tactile and vision. But if I compare your sensor to like an external camera and the tactile sensor, like a normal digital or whatever, what are the benefits in the TacThru?
Yeah, that's a good question. So typically we have other visual sensors like the wrist camera or the third-person view, but the issue is that they are far from the the two center point, the TCP, the fingers. So there will be visual occlusions due to the robot's links and fingertips. So through TacThru, you can see through your skin. That means none of the robot link will be occluding the object. And from the previous results in manipulation, you can see that TacThru provides a really unique near-field vision exactly at the object and the contact surface between the object and the sensor. So I believe that provides more detailed information concerning the object and the context. And although we only test on the parallel grippers here, I believe more application on this sensor will demonstrate more potentials in the future.
Thanks. All right. All right, so just I would place your computer over there. Perfect. No, please share just so we can keep recording. Make sure you're not you haven't enabled your microphone.
I haven't.
Great. All right. Please join me in welcoming Yunzhu Li, who is currently a professor at Columbia University, focused on robotic manipulation research. Please take it away, Yunzhu.
Okay, thank you, David. And super excited to be here. Thank you, everyone, for coming. So today I'm gonna discuss a series of works that we have been doing around the directions of scalable tactile sensing for robotic manipulation. So the goal of today's talk is very simple. So we are going to show you how some of the very simple tactile sensing mechanisms, but we are trying our best to put that sensor into everybody's hands, so that everybody is able to have access to the tactile sensor for them to do scalable robot learning. So recently, we have seen tremendous amount of resources and efforts being put into building robotic foundation models. So obviously, there has been a lot of considerations about do we use existing foundation model for robotics or pre-training the foundation model from the vision language model or video model. But if you look at all of the existing investigations, you realize there's one very, very important missing piece. Not hard to guess given the topic of the workshop. That is touch. So touch plays a very, very important role for humans to make physical interactions with the environment. For example, pick up a water bottle. Just from the image, it's very hard to see whether this is a tight grasp or loose grasp. Only the tactile response can tell you how much force you are applying. Or you are sitting there or standing there. The reason why you know that you are sitting or standing in a stable posture is because of tactile sensing from your body. Obviously, there's many other examples that we use our tactile sensing to do without even having to rely on our visual observations. So during my PhD at MIT a few years ago, we have developed a tactile glove, which was published in Nature, where we give this glove a sense of touch over the palm area. On the left is the interaction. On the right is the real-time visualizations of the tactile signal, where the thickness of the dots showing you where you have contacts, how much force you're applying. You can also see the circular contacting patterns indicating the resolution aspects of our sensor. So our sensor is made of very simple materials, which is piezo-resistant material. For any one of you who knows piezo-resistant material, it's a material that is force sensitive. The larger the force, the lower the resistance. So this is a very, very simple sensing mechanisms. And we want to push in this direction forward and to see how that can enable scalable tactile sensing for everyone. So back then, for that Nature paper, we actually have done some very interesting study where we asked human subjects to wear the glove and start to do the manipulations of and graspings of daily objects. Here, what you are seeing on the left is actually a video showing that after we have collected the data, we can hover the mouse on each individual tactile pixels over the palm area. And the color of other pixels in other areas of the palm indicating how likely that sensor is being used together with the points that's being hovered using the mouse. And basically, this visualization shows that the tactile areas over your palm areas are more likely to be used together. And when you start hovering your mouse over the fingertips, you realize that the fingertips, like over the 5 fingers, although they are actually far away from each other over pixel distance, they are also more likely to be used together. This can be very useful information for people who want to develop these prosthetic tools or robot grippers. And the globe right now is actually collected by the MIT Museum. If you have a chance to go to Boston, this will be the first thing you see when you enter the AI sections of MIT Museum. So since then, obviously, we want to making sure this kind of sensor is compatible and useful for robots, and especially how to thinking about the scaling up efforts of these tactile signals. So we first making sure we can learn visual tactile policies for robots to do manipulation and scale up both the simulation data and also the real data. Start from the first work, 3D ViTech. So this is actually one of the first work we have been doing since I become a professor. So we extend upon the sensor to make the sensor higher resolution, like a better signal to noise ratio. And more importantly, making sure this can be integrated with the robot fingers. So what we did was we integrate our tactile sensor on the robot gripper, and we did imitation learning. Here on the back, you can see the real-time visualizations of the tactile signals, which shows that the robot can rely on the tactile signal to know whether there are grips between the fingers or not in the face of visual occlusion. For the top right, the robot is trying to grasp an egg, and there will be a person perturbing the robot from doing the job. The robot knows to try again because it feels nothing between the fingers and redo the grasping behavior. It can also do precise in-hand reorientations, where the tactile sensing on the back screen also shows the precise position and orientations of the hex key between the fingers, and also bimanual coordination. So then you might be asking, what happens if you don't use touch? So for the hex key in-hand reorientation task, without the tactile sensing, with vision alone, the robot can do some reasonable in-hand reorientation. But for many robotic manipulation tasks, missing by a little actually means missing by a lot, and in the end, it will fail the task. In the second example, where the robot is trying to grasp the grips, without the touch, the robot either didn't grasp anything, or it might apply too much force, which accidentally breaks the grip. Then there's actually one very interesting observations we got when we did this paper. So when the human teleoperator collects the Visuo-Tactile demonstration data, we found during the process, it is very, very beneficial to actually give the human some visualizations of the tactile signals. Because the device itself, we use Aloha, didn't provide the human subject with haptic feedback. But by visualizing the tactile signals, this can be regarded as a type of visual haptic feedback. And we realized it can actually significantly improve the human subject's successful rates, and also the efficiency at which the human subject is able to collect demonstrations. So meaning this kind of visual haptic feedback is very handy for the human subject to know whether it's time to switch to the next a subtask, or be able to have a better understanding of the system state. Another question we typically got is actually about the sensor resolution. So our sensor resolution is about 223 millimeters. And the people are asking, how does that compare with humans? So this is actually a very famous cognitive studies I remember it was in the 80s. That's trying to understand the sensitivity of different parts of a human body. They've come up with a very interesting experiment called 2-point discrimination. The idea is to apply 2 needles and touch different parts of your body, and asking the human subject how far these 2 needles needs to be away from each other, where the human subject realized these are actually like two touches instead of one touching points. If you look at the fingertip area, it's almost exactly like the same as like 2 to 3 millimeters, which has a comparable resolution with our sensor. So our lab has been hugely benefited by many like open source like hardware projects. So we made very strong commitments and also efforts and try to making sure the sensor is as reproducible and as accessible as possible. So we released a very, very detailed reproduction guides with step-by-step detailed like fabrication like instructions for everyone to reproduce this sensor. And some people are also asking about the cost. So given our most recent design, assuming all the materials have arrived, it will only take you 2 minutes to put the sensor together and the sensor can start functioning. And depending on how many units you are like manufacturing at the same times, it will actually give you like a different price points. So sometimes I'm jokingly, even if like the PhD students are heavily underpaid, but they are still the most expensive parts of building the sensors like during the process. So it's very cheap. And we have also made a lot of efforts in trying to making sure the sensor is compatible with the low robots ecosystems, such that for people who are interested in and also have the capacity to play around with the low robots like ecosystems, it will also be as easy to put the sensors into the low robot systems for you to do like many different like manipulation tasks using the SO101 like robots. So we made a lot of efforts to increase the accessibilities of our sensor. So like since we released the sensor like a little over a year ago, our sensor has already been widely used both in academia and also in industry. So many universities across the world have been able to reproduce our sensors and give me like very, very good feedback about their experience with our sensor. They have also been able to like modify our sensors to like integrate it into different tasks and different form factors. And notably, some companies has also been trying to build commercial versions of our sensor, specifically analog devices, where they are building a commercialized versions of the sensor and has already been doing demos at, for example, GTC and UConn. So many of you might also have the question, how does the sensor compare with other tactile sensors? So this is one interesting thing about touch compared with vision. The touch is still a field where the mechanism hasn't converged yet. Many people have different opinions and different preferences about the sensor. So our sensor compared with other ones, especially optical-based ones, capacitive-based ones, like magnetic-based ones, our sensor is scalable. It can be like produced at a large scale. Some are, and also at different like sizes with different like coverage areas. It's also very flexible. So in the essence, our sensor is just a piece of paper. You can bend and stretch it like how you might do to your paper. It's also very easily customizable into different form factors. We have already shown that our sensor can be customized into, for example, globe shapes or fingertip shapes, and also some kind of like robot skins for the robot to get some more scalable understanding about those kind of contacting events. And it also have very good like robustness and consistency. So when I talk about consistency, it's about consistency both, of course, different type of use, and also, of course, different fabrications of the sensors. So one data point I can give you is that my students fabricated like 4 pieces of sensors for NVIDIA during the summer of 2024. Like 1.5 years later, they are still using the sensor, and the sensor can still enable the robots to do exactly the same task. So that speaks to the overall robustness and consistency of our sensor. And lastly, I want to also highlight this one very, very important benefit, which is the compatibilities of our sensors with simulation. We have actually just heard a Spotlight talk that uses our sensor, and they are also building like a simulators around it. So around simulations, the most important like aspect about the simulation is about the correlation and alignments between the real tactile sensing and also simulated tactile sensing. So we implemented a very, very scalable and also efficient implementations for our like tactile simulation based on some spring damper systems. So very simple, just 3 parameters for you to do the identification. And what we can achieve is a simulation shown on the right. It has very, very strong alignments with whatever happens in the real environments. If you look at this video, you realize not only does the scene states matches very nicely with each other, but also the tactile signals on the back, both in the real environments and also in the simulation, have some very, very strong alignments with each other. So besides qualitative understanding, we obviously have to understand quantitatively how simulation and real environments, they align with each other. So here on the right, we are showing a histogram. So this is generated by a human subject using the real teleoperation device to do the random play interactions with the environments. So we collected all the tactile signals in the real environments and replay all the motions in the simulation and also collected the simulated tactile signal. And we draw histograms between the simulated tactile signal and real tactile signals and trying to make sure they are aligned with each other. So this shows the fidelity of our simulation. And this kind of histogram visualization is also a very common technique for you to understand the meshes, especially in computer vision, like, for example, aligning white balances. So after you have the simulation, there's just so many things you can do in simulation. So one notable thing we did was to go through this real to scene to real loop by using scalable like simulation reinforcement learning like training procedures to fine-tune the policies to making sure it can work in the real environments. Here is one example shows that the robots equipped with our sensor and going through this real to scene to real procedures allows the robot to do like a bimanual like assembly of this like pieces from the factory benchmark. So these are actually robots in my lab. And we have also shown that exactly the same pipeline can also work on the robots like at NVIDIA. And they are also following this real to scene to real pipeline of doing the simulation fine-tuning of the Visuo-Tactile policies for the bimanual assembly of the task. So this is how we are scaling up the simulation data. And at the same time, we're also trying to scale up the real data. On the real side, like what we have been doing is also like in some ways similar to some of the other people have been thinking about. It still integrates the tactile sensors into the UMI breaker. So there's one very interesting like insights towards this process. For any one of you who have played with the UMI breakers, so it's essentially a handheld device you use to do in the wild data collection. For the human subject, because of the mechanical spring within the UMI breaker, the human subject will actually feel the haptic feedback during the interaction process. But the original UMI design never stored any of those haptic information. So only its position information was stored in the original UMI design. So that is a very important missing piece of the original UMI. So by integrating our tactile sensors into the UMI breakers, not only allows it to be very portable for in the wild data collection, but diffusing the last missing piece by storing the haptic feedback indirectly in the form of the tactile signals. We collected like a bunch of like real world like interaction like sequences. Here what we are showing are synchronized videos of both the vision shown in the first row and also the tactile like information shown in the second rows, which really allows us to do like scale up data collections in the real world environments. So after we have collected the data, we can do multimodal Visuo-Tactile pre-training, and we can post-train the policies for some manipulation tasks. Here the task is to do in-hand reorientations of the testing tube and be able to do the insertion of the testing tube in the rack. What's interesting about this video is that there's a person constantly perturbing the robot from doing the job. And the robot knows that the testing tube is not in its upright positions. It has to redo the in-hand orientations to finish the task. And on the right is the exact input to our policy, where the first row is the visual information and the second row is a tactile signal. Just from visual information alone, it's very obvious, like it's very hard to see that's the position and orientations of the transparent testing tube. But from the tactile signal, it's very obvious, like the specific in-hand object states. And that is very important for the robot to successfully accomplish this task. So we have also done many other tasks, like using this pre-training and post-training framework to do this in-hand orientations and insertions of the pencil. And also tasks require like a precise force modulations, where you want to release the gripper to suck the fluids into the glassware, but you don't want to release it too much, such that you release the pipette. So this requires very precise force modulations. And also, obviously, some classic ones of wiping the whiteboards. So this has been our efforts in also scale up the real data. So like on this front, like we have actually been releasing a lot of like open source resources for you to like play with. For example, this is our fabrication guide. It's simple but works. Where we have the, for example, bill of materials for you to follow in order to get all the materials you need. And we also have very like detailed like fabrication guides together with videos showing you how you can very quickly put the sensors together and be able to connect with the hardware in order to like read out the tactile information. We have also released the simulation environments that we use to do the simulation like a fine tuning, specifically in both like Isaac Gym and also Isaac Sims. This unlocks a lot of possibilities for you to like use all the powers you can do with GPU accelerated like simulations. And we have also put a list of like works that's built on top of our sensors. And really you can see that our tactile sensors, although the mechanisms is very simple, but starting to like grow into an ecosystems where many people are trying to build on top of our sensors for many different like manipulation and also interaction type of tasks. So in the end, like I want to actually share one like teasing works that is still ongoing, but we have actually achieved some very interesting like manipulation results, word modeling results with both vision and also touch. Here, what you are seeing is a multimodal 3D word model. So what you are seeing here is a live interactions using keyboards to control this like a robots to do this kind of bimanual in-head orientations and insertion like process. This is not real recording. This is not physics-based simulation. This is pure action conditions 3D video prediction. And this can run at 16 Hertz. And you can also see, for example, during the insertion process, you can also see the visualizations of the tactile signal, which has very nice alignments between our tactile pads and also our like a visual like a point clouds. So you can distinguish between two cases. One, where you haven't been able to have a good alignment, so you slide like over the tube. And here are second examples. Like after you have done some more precise like in-head orientation and more precise alignments, it will be able to actually insert the pieces on the right into the tube. So this shows this very nuanced understanding about physical interactions using our 3D multimodal word models that you can interact in real time. So in the end, I want to thank all my collaborators, especially my students. Without them, it will be impossible to do all the works that I have showed like just now. I would also like to thank all the sponsors of my lab, and I'm happy to take any questions. Thank you.
Thank you very much. My question is, right now we're transferring from grippers to dexterous hand. And how do you think the experience and the existing module of the sensor can be transferred into dexterous hand? Like on a scale of 1 to 10, do you think how hard it will be comparing to applying on grippers?
So this is totally possible. For example, if you see our very first work, which was published in Nature, was to build a tactile glove. Yes. So the compatibilities of our sensor is actually very nicely compatible with like hands, because the hands, if you look at it, it's a deformable like a piece. It can bend, it can stretch, and our sensor can actually have this very nice benefits of enjoying the fact that it's just a piece of paper. So be able to attach our sensors into the hand-shaped like objects or dexterous robotic hands is actually very doable. So and we are actually actively working on that. So actually to take a step further, so my students at one point think, oh, there have been so many like companies like out there that are trying to build some kind of tactile glove or like dexterous hands with the tactile sensing. Like he's like, let's just let the industry do it and we can focus on something else. And after a year, and by witnessing like all the like dexterous hands with the tactile signals and also the tactile glove, we realized they still haven't really achieved the level of performance that we feel satisfied. So right now we are actually like working very actively like internally in my lab in trying to build a very easy to use and scalable like a tactile glove for us to further scale up the tactile sensing, not only for parallel jaw gripper, but also for dexterous hands.
Yes, I also have another question. So after 10 years, 15 years in the future, when we eventually want to give robots skin, as far as I know, the sensor right now is a material that has to change shape so the resistance will change. So if you want skin that can like barely changes shape, how do you think this solution can be still applied to future skin like that?
Yeah, thank you for the question. So just to clarify, so for our sensor to obtain a signal, it doesn't have to change shape. The mechanisms of the sensors is like a force sensitive. So meaning the larger the force, the lower the resistance. So that is how the sensor is able to like obtain the signals by like sensing like a different amount of forces you are applying at different locations. So it doesn't have to bend to get the sensor. It only have to like be like compressed to get the sensing informations. So for example, like our sensor is actually can be very nicely compatible with the skins. And this is probably like one of the few like options that's like I can see for us to build tactile skins. There's many other tactile sensors like optical based ones. But because of the constraints of the optical based sensors, the minimal like sensing range, et cetera, it's very hard for me to imagine how that can be integrated as in a skin form. But because our sensor is just essentially a piece of paper, so it actually is very, very compatible with like skin, like a type of form factors.
Well, thank you very much.
Thank you.
Can I ask a question from online audience?
Yes, please. Hello, Jianxin.
Hi, Yunzhu. Very cool talk and very cool sensor. I have a question about. So I feel like the sensor is still, you said, a piece of paper, right? So I feel like it's still gonna be hard for you to nicely cover curved shape. So I was wondering, like one thing that I was very interested in is like more like fabric like sensor. What's your thought on that? Like how easy is it to have actual like fabric stretchable and you can even just cut it in pieces and it will still work? I feel like it will be easier to attach to curved surface. Yeah.
Yeah, thank you, Jianxin, for the very nice questions. So our sensor can actually be used to cover like 3D structures. If you do some kind of cuttings and like foldings, thinking about like origami, and basically you can use this kind of 2D piece of papers to cover like a different like 3D structure. But I agree with you, it may not be as straightforward as if we just use fabrics. So actually, like during my PhD at MIT, we had a paper published in Nature Electronics where we built tactile textiles. The idea is to like replace the little like fibers when you knit a sweater with the wires that are coated with piezo-resistant materials. And that allows you to obtain the scalable tactile sensing, and which actually shows in that work, it can be knitted into like directly into 3D structures, like how you knit a sweater, and it can actually obtain the tactile signals. But one thing we realized from that work is that at least that particular design has a lot of more noise than the sensors we are showing here. So there's a lot of like considerations about this kind of knitting process. For example, what material to use. And if you coat those like piezo-resistant materials over those wires, how uniform the coating are, and how likely those coating might like peel from the wires. The robustness and consistency is actually one major concerns for the tactile textiles. So that is why in that like Nature Electronics works, like one of the major innovations is to develop a self-supervised like sensor calibration mechanisms for you to obtain like a cleaner and more calibrated signals. So I think that is definitely a very, very exciting directions, but people have to thinking about the trade-offs, and much more work needs to be done for that to be like truly like accessible.
I see. There's one quick follow-up on that. Like, do you think right now, that work was 2019, you said, like, do you
Yes.
think right now is the time to revisit the concept of a fabric custom flexible tactile sensor?
I wouldn't call it revisits. Many people are actually building follow-up works on top of that.
Okay.
And I do
I see.
believe, like, given all the attentions and investment in this area, it will be a very good, like, a ways of thinking about how to further improve upon that direction.
Got you. Thanks.
Yeah, thanks, Nishi.
All right, we have time for just one more question because we want to make sure that we make enough time for the presentation.
All right, yeah, thank you for the talk. It was very interesting. One question, correct me if I'm wrong. Currently, we're not trying to detect shear forces only. Yeah. So do you think like shear forces are even important for dexterous manipulation, or do you think it will be hard to solve some certain tasks without shear forces?
So this is actually very, very good question. So our sensor itself, in its like a mechanism, it doesn't give you like a shear force, but we already actually show that this kind of sensing mechanisms can already provide you with a lot of capabilities for tasks that people traditionally believe need shear force. For them, like a peg insertion, they can already provide you with a lot of benefits for many of those tasks. So one thing I want to clarify that our sensor can detect like dynamic shear. If things like slides, you can detect that. So it just doesn't give you as like a calibrated of a signal for like a static shear. But like what we actually observe, like also together with analog devices, is that even just with this kind of sensor that's only like a sense in its like a mechanism only sense like a normal force. When the sensing resolution is dense enough, like when you are trying to trying to do the sliding over the sensors, because of some local even very nuanced and limited like compliance, can give you a very interesting observations of the shifting of the force distribution. And this shifting of the force distribution can allow you to, for them, detect shear.
It also needs to be very high frequency, right?
It also needs to be very high frequency. But that is actually one nice benefit of our sensor. Our sensor can be easily run at 100 hertz. I think analog devices achieve like 1,000 hertz or something for temporal resolutions. So yeah.
If I understand correctly, you think shear forces is not really necessary at all if you have high enough density and high enough frequency.
So let me answer your question directly. I think for many tasks, shear force may not be necessary. And obviously, there are existing a decent percentage of tasks where shear force is important. But even for those tasks, even with our current like sensor design, it can give you some approximations of the shear force. And it can also give you like a tremendous amount of benefits for you to do those tasks that people traditionally believe shear force is absolutely necessary.
Awesome, thanks.
Yeah, thanks.
All right, thank you so much, Yunzhu, for that great talk. We'll invite our next speaker, Jessica Yin. Jessica is a researcher at NVIDIA who focuses primarily on tactile sensing for dexterous robot manipulation.
Sorry, one second.
Yeah,
I'm trying to get my screen. You know how to get speaker notes? Sorry.
Not that one.
Oh, that's great.
There you go.
Yeah, good.
Okay. All right, take it away, Jessica. Thank you so
Okay.
much.
Thank you so much. I'm gonna steal this chair. But thank you everyone for being here today. I know it's like the very last session of the very last workshop on the very last day. So I was initially not very optimistic about the attendance, but it's really great to see everyone today. So as David said, I'm a research scientist at NVIDIA, and I focus on scaling dexterous tactile data. So within the tactile sensing community, there's this very famous experiment that a lot of people have used to motivate their research. This woman is asked to light a match with and without anesthesia applied to her fingers, and to study the role of tactile feedback in human manipulation. With numbed fingers, it takes 5 times longer and it's much harder. And so the takeaway from this and from many works by Roland Johansson is that touch enables human dexterity. And so as roboticists, we look at this and we're sold on the necessity of touch. So we hypothesize touch will enable robot dexterity. And so to study this, roboticists have spent decades developing and building tactile sensing hardware to equip our robots with a sense of touch, myself included. However, the majority of state-of-the-art robot systems are not using tactile sensors at all. In fact, many recent cutting-edge works show just how much you can do with a bimanual parallel jaw gripper setup. So when we look again at the promise of tactile sensing and our original hypothesis, it turns out we can actually do quite a lot without it. However, one key point is that recent works limit their systems to parallel jaw grippers, and I believe that truly general manipulation requires dexterous hands. And I do believe that that's where we will see touch as a key sensing modality in enabling robot hand dexterity. So this brings me to my overall research question, which is how can we leverage tactile sensors for the next step change in robotics? And I believe that this next step change is general and useful manipulation in human environments via dexterous robot hands. So parallel jaw grippers have taken us quite far, but they still hit fundamental limits in human environments. So when we consider these kind of everyday tasks, these all require or would be dramatically easier with the fine motor control and adaptability that multi-fingered hands can provide. And this is why dexterous robot hands are the next frontier for truly general manipulation. However, robot hands also introduce new challenges. So first, dexterous manipulation is full of visual occlusions. Multi-fingered hands create self-occlusions, which scale with the number of fingers. There are also occlusions from clutter and hand-object interactions, which cannot be resolved with even several cameras in uncontrolled in the wild environments. And tactile sensing is extremely complementary to vision by providing data exactly where these occlusions are occurring. Second, with multi-fingered hands, we also introduce both much more contact with the robot and expand the diversity of contacts that we can control. And I think manipulation really boils down to controlling contact. If our robots are not able to sense contact at all, I don't see how we can expect our robots to control it. Okay, so back to my research question. I've defined what I think the next step change is. And now I'll talk about how I think we can leverage tactile sensors. So I think currently the main bottleneck for progress in figuring out how to leverage tactile sensors is the lack of dexterous robot data. And before I go too far in this talk, I just want to clarify, I know there's no universal definition of dexterous. So I will define dexterous as independent, coordinated control of fingers are required to successfully complete the task. And we've seen data-driven approaches really dominate and push forward the progress of other modalities in research, such as, of course, language and vision. And now we're really seeing this impact in robotics. But we have not really been able to extend this to the tactile modality for dexterous robots. So why is this? Well, obviously, dexterous tactile data is really hard to collect. And so, for example, dexterous tele-off data is really expensive. It's really hard. You need these really excellently engineered systems. You need a lot of experience. In sim, getting rich contact signals, which frequently occurs in dexterous manipulation, is really difficult. For RL, these dexterous control policies can be hard to learn due to the large action space of high-dop hands. And with human data, the data sets we have are really dominated by vision-only data like videos. So my recent work has focused on the question of how do we scale dexterous tactile data? So today in this talk, I'll cover how we can scale dexterous tactile data in both the real world and in simulation. So first, we'll take a look at real world data. So I'm going to start with the statement that generally, I think humans are a really promising source of scalable real world data. And why is that? Well, I think the fact that human data is really plentiful, which is enabled by a lower barrier to entry for data collection by non-experts, non-roboticists. There's not actually that many of us in the world. So this really helps a lot with scaling. there's no need for years of robotics experience and really, really fine-tuned teleop stack just to start collecting data. And we also have now really cool wearable devices coming out, like the Arya glasses. We have a lot of data sets focusing on human demonstrations and millions of videos on YouTube for robots to learn from. But even though we have all these wonderful human data sources, they are primarily dominated by only one modality, which is vision. And that's not enough. We also need human tactile data as well. And I think another argument for using human data is that compared to robot morphologies, the human morphology is very, very slow to change. It's very stable. And we all know that robot hardware development has really exploded in the past few years, and this is really great for our field. And I really hope that we continue to rapidly iterate on our hardware. But on the data collection side, this iteration speed from hardware can be challenging to cope with. So, it can be a very serious time commitment to collect a large data set or invest in teleop infrastructure or tune a SIM model or deployment stack for the next best robot platform. So I would argue that the human form as a very stable morphology could and should be the universal embodiment for real-world robotics data. Okay, so let's take a look at this case study of just ironing clothes. Tactile feedback here is beneficial for the task itself. You can kind of feel the bends and seams through the iron. And tactile can help resolve ambiguous hand poses from occlusion, such as my fingers around the iron handle. However, this is a really difficult task to tell because it requires a lot of precision in the time domain. So specifically, the failure cases here are that, if you're ironing too slowly, then you'll burn the fabric. If you iron too quickly, you actually fail to remove the wrinkles. And so if I want to collect tactile data from this, or really from any other task, this would be my wish list for dexterous tactile data collection from humans. So the first one is unrestrained human dexterity. So this is, I think, the #1 factor in both ease of use and time efficiency of collection demonstration. The second is rich shear normal force sensing, since we know that both of these provide important tactile feedback. The third is full hand coverage. So the fingertips, they get a lot of attention from the tactile sensing in community robotics, but it's also important to consider that, as us humans, we really intuitively leverage our palm and our whole hand when doing things. For learning a policy later, it's necessary for this approach to be compatible with in the wild tracking methods. So basically like not mocap or not restrained to a lab environment. And finally, if I want my robot hand to easily benefit from tactile feedback at deployment time, it would be great to use the same human and robot tactile sensors for both data collection and deployment. And our community has made a lot of progress towards achieving this. So I've compiled a comparison of how some state-of-the-art gloves stack up against my wish list. Although I know there are actually a lot more gloves out there now in the past few months, but unfortunately my wish list from these are not fully satisfied. So here I'm excited to introduce the Osmo Glove, which is an open source tactile glove to study how robots can learn from humans. And so here we show where the tactile sensors are on the glove. And so we designed this glove to fulfill our wish list for what we want to see in tactile collection devices. So first, it has 3-axis force sensing. It has full hand tactile coverage. We have compatibility with in the wild hand tracking. We preserve and capture human dexterity. And this glove is deployable in robots. And now I'll dive a bit deeper into each of the core features of the Osmo Glove. So the first, which is the rich tactile data, this glove uses a magnetic sensing principle. And how this works is that we basically place a magnetic skin on top of a magnetometer. And when the magnetic skin deforms, the magnetometer measures 3-axis magnetic flux, which is strongly correlated with normal and shear forces. And this builds a lot on the work of reskin and AnySkin. And so here's an example of what the tactile data looks like from just one fingertip. For example, the middle finger, which is mostly occluded throughout this entire video, but you can see how rich the tactile data is here. And for in the wild hand tracker compatibility, the Osmo Glove broadly supports vision-based hand tracking. So we chose this beige color because it's in distribution for a lot of RGB hand tracking models. And the Osmo Glove has a low profile form factor, so it doesn't have like huge electronics or exoskeletons or anything like that. That both minimizes encumbrance and visually looks like a hand, like a human hand, so there are no modifications needed to hand tracking algorithms. So in this video, what I want to highlight is that this is something that just works. So here I'm just donning the glove. I have the Quest. The Quest just picks it up as a hand, and you can qualitatively kind of compare how the hand tracking works compared to my left hand. So yeah, Quest tracking is not 100%, but it's not qualitatively worse than a bare hand tracking. And here are some other demos with other wearable headsets like the Apple Vision Pro, the Aria Gen 2, Quest 3, which all have the device's native onboard hand tracking estimates overlaid, and the glove is worn on the right hand. And there's also an example with RealSense and DinHammer, so it doesn't necessarily need to be an egocentric or a specialized wearable device. You can also use an externally mounted camera and off-the-shelf hand tracking model as well. And for hand tracking through occlusion, we also integrate the Osmo sensors with the Manus hand tracking glove. So where even though the Manus gloves, if you know those gloves, they use electromagnetic sensors for fingertip tracking, but our sensors actually do not interfere. They operate in different frequencies. And finally, the Osmo glove is deployable on biomimetic hands to minimize the visual and tactile gap. So this is really convenient because this feature minimizes, this essentially lets us not do any special vision in painting or overlays or masking at all. You can directly use data that you collected on the human with the glove and just deploy that on a robot wearing the glove. So, and also because, so this is the psionic ability hand wearing the glove. And because I'm using the same glove for data collection and deployment, the sensor locations, the data format, the noise characteristics of the glove are the same, and visually they're also the same. Okay, so what does data collection with Osmo look like? Here we have one RealSense camera to track the hand pose, and we're collecting tactile data from the Osmo glove. And we chose wiping as our task because it illustrates how many different applied forces can result from nearly identical visual images. So look at how much variation there is in the tactile signals with minimal changes in pixel space. With about 2 hours of human Osmo glove demos, we can train and deploy a policy on a robot system without any robot data. In this work, we follow a pretty standard human to robot policy pipeline. Honestly, not that special or interesting. Essentially, we convert all of our human trajectories to robot data with reverse kinematics. We construct our data set from the retargeted trajectories, and we directly use, without modifying, the RGB images and the tactile glove data from the human. Then we train a diffusion policy. So here it is. For example, this is trained with this data, and now we can deploy with a robot wearing it here. More details in the paper if you're interested. So to briefly summarize, we built the Osmo glove to realize our vision for how we can collect dexterous tactile data. And I think beyond the actual hardware, I hope that sharing our vision for what wearable tactile glove design principles should be is what I think is the main takeaway from our work. And like I said, this is all open source. It's available on GitHub, all the code we used for data collection, training, and deployment. I also get some questions on is this going to be off the shelf, available for purchase? And I am working with a manufacturer in China to hopefully get this up and running. Hopefully maybe by the end of this year, but no promises. So hopefully this will be another option to purchase later. Okay, so one of the obvious next questions is, what if we want to deploy on a robot hand with different tactile sensors? So say, for example, you update your tactile sensors to be more reliable or a newer iteration. You don't want to throw away all of the data that you previously collected with the tactile glove. So for this, we introduced Tactiline, which was presented earlier this week at RSS, led by Yunzhu Li, who's now at Google DeepMind. So with Tactiline, we propose a method for cross-sensor tactile alignment for cross-embodiment policy transfer. So we assume the human is wearing the Osmo tactile glove. So here it's integrated with the Manus tracking glove for non-visual tracking. And we learn a tactile alignment method to transform the human tactile to the robots, and thus enable robot policy learning with the human data. The key innovations with this work is that there's no strictly paired or labeled data, and we support dynamic interactions for tactile alignment. So it's not purely static interactions. So our approach is that we collect an unpaired human and robot data set where there's overlap between the same task and some of the same objects. Then we independently learn self-supervised tactile latent distributions. And then we learn a human to robot tactile feature mapping via pseudopairs within the same task and object. So here we show all the policy rollouts for this insertion task across different object categories. So with randomized grasp, our policy can successfully recover from misalignment and jamming by leveraging tactile feedback. And then this section is about our lid closing policy, where we show that tactile alignment can help. Again, with randomized grasp, the policy uses tactile feedback to perform search, alignment, and closing between the lid and the bottle. And as shown in the video, our method enables the policy to effectively recover from misalignment using tactile feedback. So again, these are different. So these are the Zila sensors, and then all this data was collected with the Osmo sensors. Light bulb, and here we demonstrate with human data only, no robot data used for this task at all. And so light bulb screwing is a particularly challenging task because it involves in this case, severe occlusions from the lampshade, and the bulb is small relative to the robot fingers. So as a result, collecting a robot teleop dataset without tactile feedback is pretty difficult. On the left, we show the human demonstrations where only 10 minutes were used to collect 20 trajectories. And we have no tactile baseline, which failed to make contact with the bulb. We also have no alignment baseline, which made contact but frequently jammed. And then in contrast, our full method achieves robust and stable light bulb screwing. Okay, so for the main takeaways, we introduced the Osmo Tactile Globe as a more scalable way to collect real-world dexterous data from humans. We have the first iteration in terms of the hardware on a set of design principles that we defined for wearable tactile glove development. We also introduced TactiLine for cross-embodiment transfer between humans, robots, and different sensors for data collection and policy deployment. And we also show that the Osmo Tactile Glove data can be zero-shot transferred from human to robot embodiments, so with tasks like wiping and light bulb screwing. Okay, so now that wraps up the real-world data section. And now we'll talk about synthetic data, in this case, tactile simulation. So we've seen how RL really excels in this problem space of dexterous control with new breakthroughs in fundamental in-hand dexterity skills like object rotation. However, if you look a bit more closely, you'll see that typically they don't use any tactile sensing, or they use highly simplified tactile outputs. And in these works that do use binary contact, they've shown that tactile feedback enables significant improvements in performance and robustness. However, we know that our tactile sensing hardware is capable of providing much richer data than just binary normal force. So this begs the question, why are people not using tactile sensing? What is the bottleneck, and how can we unlock rich tactile sensing for sim-to-real RL? So what's the bottleneck here? Well, RL policies need a lot of data because they're super sample efficient. And if you were to generate this data on a real robot, you would need months of data to learn a policy, learning from scratch. But in simulation, we can produce all of that data in just a few hours. So we have to use, fast GPU parallelized simulators for RL to be a tractable approach. And IsaacGym or Isaac Lab is kind of the gold standard here. But IsaacGym's speed is possible, at least partially, from using simplified contact models, such as rigid body and point contact assumptions. However, we know that these simple contact models are not realistic. For example, we know, our tactile sensors are soft, they're not rigid, and contact occurs over this entire area, not just this little point. And unfortunately, this leads to unrealistic tactile signals, since tactile signals are directly derived from the contact models in simulation, which creates a sim-to-real gap for tactile sensors. So this means that generally speaking, rich tactile signals generated natively in IsaacGym are not transferable to the real world. So taking a closer look at this problem, when we look at this in-hand translation task, we can observe that the controller is leveraging sliding contact between the cylinder and the palm of the hand. So it'd probably be useful here to add some sort of tactile feedback about the sliding. So let's say we add this tactile palm sensor. But when we simulate these tactile signals natively in IsaacGym, we have really, really sparse signals, almost zero the entire time, even though we know that shear normal forces are definitely not zero. So these sparse signals are from the simplified physics because we're relying on collision geometry penetration to activate the simulated tactile sensor. And so now the question is, how can we harness the speed of IsaacGym or simulation while producing useful tactile feedback? So our primary contribution in this work is enabling rich tactile feedback for RL frameworks with a sensor model that is tractable for RL and zero-shot transfers from sim to real. So we go beyond the binary normal contact that we've previously seen and use all three axes of force feedback that our sensor reskin provides on the palm. And specifically, we achieve 70% of the training speed compared to proprioception only policy. And second, we evaluate the effectiveness of this sensor model with over 190 real-world experiments. We demonstrate with the task of in-hand translation, which leverages shear sensing to capture sliding contact. Okay, so how does our sensor model work? I go kind of fast through this, but essentially we have like reskin on the palm of the Allegro hand, and we discretize the palm to 16 taxels, each of which correspond to a magnetometer. And then we model each taxel as a rigid cylinder, but we extend the sensing range R to essentially capture object contact without a rigid collision, which kind of allows us to approximate an interaction with a more compliant volume. Then to represent the object, we sample points from the surface of its collision geometry, and each point I within sensing range contributes to the sensor signal, which allows us to calculate the signal with intersecting contact volume, in contrast to using the typical single contact point per two-body collision approximation. And then we sum the penetration distances, and okay, these details are in the paper. It's not that complicated either. But essentially, we do have continuous signals from this model, but we don't quite have sim-to-real transfer for the full continuous signals. So here we use a signed Turing version of shear and binarize the normal forces as well. And so here we show that our model can achieve richer signals compared to the default simulator output. And just to be clear, we haven't changed the underlying physics engine of Isaac Gem or PhysX, but we still use the simplified contact to retain tractability for training RL policies, but we are modifying the sensor output to more closely match the real signals. We deploy on the real hardware system. We find that it helps with out-of-domain hand tilt and adaptation. And we also find that it works well on new objects like this water bottle where this center mass is changing throughout the task. And after over a bunch of experiments, we find that our 3-axis tactile policies generally provide the best task metrics. And we also find that these policies generalize really well to different objects that we didn't train with. Okay, so sorry, I'm trying to go past this slide. Okay, so our takeaways from this work is that when we combine this tactile feedback with proprioception, we find that it increases task performance and enables superior policy adaptation. And I think the main thing that we're trying to communicate here is that all of the simulation that we're doing needs to be RL tractable. So my dream would be to make tactile sensors as easy to simulate and universal in RL training as training with robot proprioception or camera images. And a huge part of that is just the speed. So I just want all roboticists to be able to simulate tactile without even thinking about the cost, whether that's wall clock time or GPU memory usage when you want to train policies. Okay, but that's just binary 3-axis tactile. And ultimately we want continuous 3-axis forces and to be able to simulate the full resolution of what our tactile sensors can capture. And the problem of high fidelity tactile simulation is intrinsically intertwined with the contact models available in simulation, right? So as I said earlier, PhysX is amazing for speed and RL tractability, but it can be difficult to get continuous, smooth, realistic forces directly out of the physics engine. But I am really excited to share, if you haven't heard, that our teams at NVIDIA are developing a new physics engine called Newton. And something that I'm really excited about is the implementation of a GPU-friendly version of hydroelastic contact. So instead of using point-based approximations as we were before, we can now simulate full hydroelastic contact surfaces, which gives us much more physically realistic contact behavior and therefore tactile simulation. So what is hydroelastic contact? Just a brief overview. So this model is a contact model pioneered by TRI and Drake in 2019. And this allows us to capture the area dependence of contact while neglecting deformation effects. So this is a really key approximation and design choice of the hydroelastic contact model. So the bet here, which is explained really well in TRI's blog post, is that we don't actually need to simulate the full mechanical deformation for most contact interactions for roboticists. However, it's still helpful to kind of have this contact surface for realistic forces. And so this is where hydroelastic makes the trade-off between speed and fidelity. And so how the model works in the original formulation is that each object is a composition of tetrahedra that stores pressures. And hydroelastic contact finds the contact surface as the isopressure surface between pairs of tetrahedra. Then the simulator integrates over all polygons of the isosurface to get net wrenches. And in Newton, essentially what we do is we just make it a more GPU-friendly version. So for example, we replace tetrahedra with sparse SDFs and a lot of other optimizations under the hood that makes it a better fit for GPU processing. So this GPU-friendly version is led by Leonard Rostel from TU Munich while he was an intern at NVIDIA. And we also have this recent ICRA workshop paper for more details. And so intuitively, when I look at hydroelastic contact, and I look at high spatial resolution Visuo-Tactile deformation images, they literally look the same. So it's a very natural fit in terms of what we're measuring, what we're simulating here. Obviously, this idea is not that new. As we saw earlier from Mustafa and earlier in this week with An and Jaejun, hydroelastic tactile sim has been explored a bit, as well as this work in Machoko, but perhaps it's a bit underexplored. And I'm excited to share that we are actively working on leveraging hydroelastic contact in Newton to co-develop a high throughput and high fidelity tactile simulation for Sharpa wave hands. So I'm leading this partnership with Sharpa, which I'm super excited about. And we're looking to really enable and unblock sim-to-real tactile RL research with Isaac Lab and Newton. So we have some very early initial results. This is still currently under development, but we've done some initial looks at comparing how Newton hydroelastic is doing compared to the phys-x forces. So here phys-x is the orange line, hardware ground truth is the black dashed line, and Newton is the blue curve. And so we're already seeing a much better fit in terms of continuity and matching hardware. And we also have here some initial results with the deformation map. So this is the full 240 by 240 pixels output from the tactile sensors integrated in the Sharpa hands. And so you can see qualitatively pretty good sim and real matching. So yeah, just excited to share NVIDIA and Sharpa co-developed tactile simulation coming soon. Again, we are really looking at high throughput in terms of optimizing speed, environment steps per second, GPU memory usage. Looking at high fidelity, we want to enable zero-shot sim-to-real tactile transfer for Isaac Lab and Newton. So in conclusion, this kind of covers my work. Sorry, I went a little bit over time. And with scaling real-world dexterous data as well as tactile simulation, I want to quickly acknowledge my collaborators. Of course, this work would not be possible without a lot of people at Meta and Penn while I was there, and also my team at NVIDIA. And I just wanted to share that I'm also part of the Dex team at NVIDIA. So we develop superhuman dexterity for robots. We're always looking for talented interns, so you can feel free to shoot me an email if you're interested. And I also had a list of hot takes or opinions because this is a workshop, so I wanted to make it more interesting. It's also right before the panel, so maybe we can talk about some stuff. But I don't think I have time to go over it, so I'll just put them up on the screen. Thank you.
Do we have any, I think we have time for 2 questions, but I do want to make sure we're set up for the panel. So is there a couple of quick questions that we can ask before going into the panel?
I'll keep this quick. Thanks for the great talk. On the glove that you talked about in the beginning of the talk, that was an awesome vignette with the iron. I'm wondering, what is your saturation limits and bandwidth for sensing on that? Can you sense like really high forces that might be necessary when you're ironing clothes?
Yeah, that's a good question. So I think we characterized in the paper that we can sense from like 0 to 80 newtons-ish. So it's pretty high. I think most human manipulation is like 0-ish to 40. So yeah, it's a sufficient dynamic range for the forces that we've seen.
Awesome. Thank you.
Yeah, thank you.
Hey, great job. So I'm curious about the cost of this glove, just for that, and also how easy it is to replace, you tear it by mistake or wear and tear and things like that. So I'm curious about those aspects.
Yeah, so the cost, I mean, it also depends on batch size, like as we've seen. So most of the cost is in the PCBs. And so when we were working with batches of around 20, it was probably around $400 total. I'm hoping that mass manufacturing or like larger scale manufacturing will bring the cost down. So yeah, so I'm not completely sure. It also depends on like how much the manufacturer wants to charge on top of it. So I don't actually know the final pricing yet. And then in terms of the wear and tear, so something that is actually kind of nice. So we have a 2-layered glove system. So one layer is like your next to skin layer, and that has the electronics directly glued on top of it. Then we put another layer directly on top of that, and that kind of like preserves that visual like appearance of a human glove without any electronics on it. And so that outer layer actually protects the sensors from a lot of wear and tear. So I use the same glove from start to finish of the paper, which is a long time. But in the event that you are interested in repairing the glove, I would say that I would probably recommend disconnecting the sensors and replacing it with another sensor package. And I think that's pretty doable. Yeah, thanks.
All right, join me in thanking Jessica.
Thanks.
Okay, so now we have a panel. Yeah, we'll have one more chair over there. No. All right. I'm going to do about 12 things at the same time here. Okay. Share. That Mark is also online, which is great. All right, we have a wonderful panel of speakers, and I encourage the audience to ask some questions. We're going to ask just a couple of questions that we prepared beforehand, and then go into some audience questions. And again, thank you for Mark staying up so late to keep us company and answer some cool questions. So the future work problem, Mustafa in his talk noted that tactile is always in the future work section but never integrated. Why has the field been so slow to make touch a first-class citizen? And what's the one thing you would change to make that better?
I think I can start. So I think one thing is that we actually haven't really seen a really strong motivation for why we actually need tactile sensing in our systems. So adding tactile sensors is always a lot more work in terms of robot system integration, in terms of maintenance. Our field hasn't converged on tactile sensors. And so I think this kind of relates to one of my points on the opinion slide, which is oh sorry, sorry, I was skipping one. This kind of relates to one of my points in the opinion slide, where I think that the current amount of interest in tactile is very tenuous and fragile, and I think we need to demonstrate real world economic value within the next few years to see sustained investment in this field. And in terms of what we can do to address that, I think one thing that we can do is try to converge, actually converge and make really focused effort on making one sensor or two sensors and one or two data formats and really make that work across hardware, across simulation, across how do we manufacture these consistently reliably, and how do we integrate those signals into learning.
Yeah, I pretty much agree with Jessica on this. So basically, like I mentioned, touch right now is very different from a vision. It hasn't converged, and not only isn't it converged, but different sensors are actually measuring, I would argue, quite different things. There are works that trying to understand even between tactile sensors, how do they complement with each other? How do they, for them, overlap with each others? And they also have different kind of form factors, and different form factor also limits their use and also comparisons in the same task. So some tasks are designed or set up in a way that is doable for one type of tactile sensors, but possibly not for the other type of tactile sensors. So this actually makes a comparison also hard. And also to use tactile sensor, you not only just need computer science skills, you also need people who have some decent understanding about the material science, some decent understanding about electrical engineering to put the sensors together. So that's the knowledge gap is also something that preventing touch from becomes more I would say mainstreams or first-class citizens. So any efforts along any of those directions on trying to build tactile sensors that are as easily to use or as accessible as possible, I think are definitely good efforts. And how to build an ecosystem around it, such as when someone want to say, okay, I want to integrate the touch into our systems. It doesn't take a month for them to get into all the nitty-gritty details of fabrications. of building all the gels, like during that period, if someone wants to integrate touch, if at that point, maybe just a day of work and touch is integrated and it's so seamless that they can do the same tasks they would do like without the touch. So I would think at that point, like a touch will become like much more prevalent than where we are right now.
Do you have any thoughts?
Sorry, is that to me?
Yes.
Yeah, I mean, with tactile sensors, we're sort of like people were in vision in the late 1960s, where they were hand wiring CMOS sensors onto circuit boards. And, you know, or not, no, I'm not CMOS, CCD. And so there's still a bunch of different types of sensors out there. And it's you know, it may just always be that sensors are somewhat application specific, and so we have to expect that integration will proceed more slowly. On the plus side, the availability of pretty good tactile sensors is vastly better now than it was even 5 years ago. And so the ability of people to make use of that sensing is also much better.
Are there any takes from the audience that anybody has any additional perspectives they want to add? Yeah.
Yeah, so we just discussed like all of the different types of sensors, right? Both in the talks of Jessica and Yunzhu, but Mark, you discussed about like in humans where each sensor has like a lot of different mechanisms with data, right? High frequency, low frequency, high density, low density. So when we try to do like generalist policies and not like task specific, will we eventually converge on this type of sensor, like not that contains a lot of different mechanisms?
I mean, I think you have an interesting point. I think another point, which is still kind of underappreciated, is the importance of timing, of salience. That understand, you know, maybe the details of the tactile information are less important than knowing it occurred at a certain time correlated with a certain event that's important for the success of the task.
Are there any other quick audience questions here?
So since it's a workshop, I thought, I ask questions which are a bit harder. So are we there yet? Are we there that we can converge to a particular sensor design? Because as Mark was saying, there's things like thermal and all that, and all the other properties that are not so well or underexplored within our space. Have we found out enough? Is the science ready that we can then converge to particular sensor design that you think will last us for the next few years? Because I don't know what the iteration might be like, the systems. Are we ready to design? So there's a lot of stuff around tactile sensors like wiring, which can be very painful. And so I'm curious about, do we all have that? Do we have that figured out enough that we can do this?
Honestly, I don't think we're there yet. And so on that front, I would say like different people are still choosing like a different type of tactile sensors depending on what kind of tasks they do, and also depending on what tasks they do. They might actually prefer a sensor that's, for example, like we do, like we only offer like, for example, normal force. Some might argue like shear force is necessary. Some might argue vibration is necessary. Some might argue like a temperature is necessary. So there's like many different ways that you can draw inspiration from human and design the sensor and also the task that is like specifically like tailored to show the benefits of that sensors. That has been how the field has been kind of like over some period of times. So I would say like going forwards, if the efforts, like I'm just like thinking out loud here, is trying to really like do some kind of convergence of the sensor. Maybe we have to first think about the convergence of the tasks that people might want to do, like or at least to show that after we have done this set of tasks, we are sort of like getting closer to making claims about the robot's capabilities in the real environments. And maybe at that point, people can be more converged in terms of how some of the aspects, different aspects of tactile sensors, some may be like necessary, some may be less necessary, especially given the trade-off of all the complexities around integrations of those like sensing like mechanisms. So I would say we are not there yet, and there might be some steps we have to be thinking about before we converge into the tactile sensor that everybody agrees on.
I think I have like 3 thoughts, I think. So I think the first one is like, I would not let perfection be the enemy of progress, or whatever that quote is like, where like we might not be ready, but I do feel this urgency to really keep the tactile field alive, especially with the interest. And so I really like would hope to see that, like, yes, I think there is a lot of scientific value in studying what is the optimal sensor format and so on. And that's something I'm interested in personally, like with maybe large scale simulation studies and ablations. But I think it is important to like kind of commit a little bit into one direction and try to push the field forward with even imperfect sensors. I think another point is that we might already be starting to see some convergence with like what can actually be mass manufactured by robot hand companies. So like basically like essentially what hardware can be scaled, and so like then maybe we just stop working on sensors that cannot be scaled, like that kind of thing. And like and working with I think industry and robot hand manufacturers I think can be a really impactful way to like kind of like nudge the tactile data into the right direction or to converge in that way. So for example, in NVIDIA, like one thing that happens a lot is like, a lot of companies come to us and we're like, okay, how can we put our sensor in Isaac Lab or Jianxin? I think one way to kind of like force some convergence is say like, your sensor needs to be able to be modeled with hydroelastic contact and like work with them to make that, to set those design requirements for hardware.
So I do have a comment on this actually. I think that in all the time I've spent working on uni-style problems, I've noticed a massive trend to focus homogeneously on visual data. I think we've seen some excellent work expanding on that in this workshop today. But multi-sensory information, and not just on the input of our models, but output of our models, is going to allow us to have better expressiveness of what behavior needs to be. And so whether tactile is there or not, there is a huge strength to building better representations to solve problems today if we're just leveraging this both on the input and output of our models. I really liked what Yunzhu showed with learning these more dynamic world models, bridging almost using like a synthesis of multiple representations together to verify that things are correct. That kind of debugging power, I think, is going to be very powerful for us in the future. Eduardo Capiello asks, how transferable are tactile sensors across payloads, 0.5 kilograms, 5 kilograms, or 50 kilogram manipulation tasks? Any comments?
That I would like to argue is another limitation of many of the existing tactile sensors. So I'm showing like our sensors, the piezo resistive ones. Many people are asking, okay, like what's the range of force you can measure? So my answer was typically very like nuanced in a sense that we can change the dynamic range. So there can be some resistors on the board you can change such that the sensor can measure like a different range of force. So if, for example, your task, you do some more fine-grained stuff, like you can change it such that it measures that range. We have also shown that like we are actually using the sensors as a carpet to measure like human weights and human like activities. You can also change the sensor to do that. So there actually involve a decent amount of manual work in order for the dynamic range to be adjusted. So we have also been thinking about, are there any ways we can do like high dynamic range by doing some kind of compositions of the sensors, but that was never implemented. Like I said, for this thing to be implemented correctly and and in a very like a solid way, it really requires a lot of efforts from people with all different kind of backgrounds to work together to make this a solid like progress. So so this is just talking about our sensor, and I have been also using many other sensors like gel side, etc. They all have the same issues. Like the range of force they can measure is sort of limited by a specific design of that sensor. It's not as easy to just go from 0.5 kilogram or 5 grams to like 50 kilograms.
Yeah, I also wanted to add that I think this is more like a sensor, like a fundamental sensor like question, I guess. So like, you know, like all sensors will have limitations in their dynamic range. I also think like the sensor response can be tuned so that you have a nonlinear sensitivity. So for example, you might want to really capture that like 0 to 1 contact event when contact just occurs, and you're highly sensitive in that range. And for larger forces, it might not be actually that important to know exactly the difference between like 40 newtons and 45 newtons or whatever. So like, I think that's something else that can help with adjusting the actual like sensitive range. In terms of like what target dynamic range we're looking at, I think something in the realm of like what humans use is pretty reasonable, and I think most sensors, I think, should be able to do that that exist today.
Yeah. And as we saw, biological sensors do have exactly that nonlinearity.
There's a question in the back.
I'm curious if you guys think that audio could be a useful addition, or do you think it's just going to be a distraction? They just put a super simple, cheap microphone, you know, on the glove.
I think audio can actually be. Oh, Mark, do you want?
Yeah, I would support it. I think I mean, first of all, it's already been used successfully on UMI, the contact microphone, and it makes a difference. And it contact audio is actually very close to what we get from our dynamic tactile sensors. Again, it's I mean, you have to implement it right, but the salience of those bursts of information can be quite helpful. That's my opinion.
I'd also like to argue, I think the audio can also be very useful. There has already been a lot of work at showing that audio can provide complementary informations to many of the like manipulation tasks. Like Mark mentioned, like there's like a UMI with integrated like contacting microphones. But if you also really thinking about like humans like the use of different sensory modalities. Like one example I love to give is, for example, if you do some kind of cutting tasks. If you do the cutting of carrots, like your eyes see the knife going through the carrots, and you actually like feel the haptic feedback of the knife like touching the boards. You're also hearing the sounds of the knife like touching the boards. So there are a lot of like information that are reinforcing each other and also complementing each other with each other that make you like to learn this kind of multi-sensory representations of those interactions in a much more like effective way. So I believe audio can be important. Like cutting is one example, like pouring is another example where you hear the audio information like changes its pitches like over different like feeling levels. And there's many examples like that.
Yeah, thanks for the question. I think I will be the villain here, and I will say that I think it is interesting, but it might not be the most urgent problem in terms of what kind of wearable tactile data you want to capture. Also, in terms of like what is available at deployment time for your robot to use, like do you even have policies that can respond to that type of high frequency tactile data? I don't know. I mean, like I think even like our policies run like pretty fast, and it's like 60 hertz. So it's like still quite slow. So like you can capture the data, but can you actually react to it in terms of measuring like really dynamic like vibrations and stuff like that? So I don't know. I think it is interesting for sure as a research direction. Impact within the next 2 years, I don't know.
Yeah, like we already see disagreements on different like sensory modalities here.
I want to add one more perspective. Audio is readily available on the internet as an intermediate representation that is often underutilized in a lot of existing works. And tactile comparatively has a lot fewer demonstrations. So in terms of good foundation model representations for even ambient audio, it can be very helpful. I think one of the things that is a common theme through a lot of the work that we have seen today is that we're trying to reduce the ambiguity of finding a salient solution through the behavioral space that we're defining. And so it's beneficial to just disambiguate certain classes of problems, just leveraging that ambient audio, let alone the kinds of interesting contact microphones that we could be using for this as well.
Yeah, I don't think we need to respond at millisecond rates to dynamic tactile or audio information. I think the value of it is often diagnostic. I mean, people don't respond very fast either. You saw in the old data I showed that the incipient slip response is 80 milliseconds. 80 milliseconds is a long time by robotic standards. Sometimes it's just the point is that information is useful even if it's after the fact, in order to diagnose that a task is going correctly or not correctly.
Great. I think we have time for one more question. Any questions in the audience or online? Okay, I'm gonna riff another question. You have your dream tactile sensor at your disposal. What is the number one feature it has to unlock the things that are frustrating you the most with your research right now?
I would say like the dream tactile sensors should be the most available tactile sensors. So if now I want to use the tactile sensors, how fast can I use it, and how easy I can integrate it, and how easy I can have all the infrastructure around it that is as easy to use as possible, like a camera. If you now want to give the robots some kind of visual information, you buy the camera, you do the integrations. You also have simulation to simulate the visual informations. And if at some point the tactile sensors can also be like that, especially with some kind of consensus around what modality of information does the tactile sensor captures, and I think that would be my dream setup.
Okay, I think I might be biased a little bit, but I would say the ideal tactile sensor is easy to simulate. And I think that like encapsulates a lot of other features. Like for example, it's like very consistent over its lifespan. It's very reliable. The sensor response is easy to model. I think those are key features. And I think also like having that I don't know, like availability or like the fully modeling the sensor and simulation would actually really let us like do these like large scale task studies that find out like, actually what is the optimal tactile sensor layout? What is the optimal tactile data format? Like across a lot of different tasks, like where is the tactile sensor most useful? Where is it not useful? Like overall, like can we actually make a statement about how tactile sensors can and should be used for manipulation by studying that in sim? Because I think in the real world, it's a little bit, it's like it's just not enough data to like, and it's really hard to like get enough data to like really say something like that. But yeah, that would be my dream.
Mark, do you have a dream tactile sensor?
I mean, for the tasks that we do, what do I need to know? I need to know contact location because that tells me where and how the tool is in the hand when I can't always see it. I want to know contact forces. I want to know when they change. I want to know when there's sudden changes in conditions or forces, because that tells me if the tool that I'm holding has made contact with something else, or if the tool is slipping, or if I'm turning a screw and I've reached the bottom of the thread and it just won't turn anymore. All those things are accompanied by a sudden change in forces.
All right. I want to take a second to just thank our amazing panelists. It was just such a pleasure to have them not only talk in front of us just now, but also the presentations earlier. So please, a round of applause for that. All right, we have one last thing that we all need to do, and that is an award, a series of awards that we're going to give out to some standout papers that we had submitted to the workshop. And so these were selected from the submitted posters and papers to this workshop. And so we have 3 awards that we're giving out, 2 runner-up awards from Ant Group and 1 Best Paper Award from Ray Institute. And so I want to first congratulate our first runner-up award, Heterogeneous Tactile Transformer. I invite any of the authors of this work up here, and I will hand you the piece of paper. A round of applause, please.
Why not? Apart from the paper. Yeah. Yes, that's for you. That's for you.
Thank you. Congratulations. All right. Our second runner-up was TacThru, Simultaneous Tactile Visual Sensing for Multimodal Manipulation. Are there any authors here at the workshop? If not, we will send the award home to them, but congratulations to them. All right, and then our Best Paper Award is OmniTacTune, Policy-Agnostic Real-World RL for Tactile Residual Adaptation of Visual Policies. Are there any authors? Oh, I saw a poster for this. Okay. Well, congratulations to them.
I think the author is online.
Is the author
maybe,
online?
Yeah, maybe you wanna make them panelist.
Yeah. Yeah, just give me a second. Can you open the? Yeah. Can the author please raise your hand
and turn on their camera?
Yeah, there you go. Panelist. I'm just waiting for them to all right, and we can take a quick photo. Oops.
Can I? Yeah, the Ray group is how to, don't know, is this?
Nope. Just there you go.
Oh.
Hey David, do you wanna go back to the previous one, like the runner-up, or maybe that?
Yes, that's a good idea. Yes. And then TacThru, can the author please raise your hand?
Put the logo on the left top of the sponsor if you want, like if they want.
Yeah.
If not, it's all right.
Yeah, that's better.
Yeah, I'm here. Thank you for doing this.
Thank you, everyone.
Awesome. Thank you.
All right, and I want to once again thank all of our sponsors for helping make this workshop possible. And additionally, I want to thank all of my co-organizers. Without all of you, it wouldn't have happened. I think it was a lot of work to put all of this together. And so just one last round of applause for all the hard work.